Hey, how's everyone doing? Good to see you all here. Where's everyone calling in from? Oh, nice. New York, Morocco, wow. Buffalo, Toronto. Nice, nice. I saw a lot from Toronto. Um, we at Headstarter were planning to go back to Toronto and the Waterloo area in just a couple of weeks. So we love it there, except for the weather. We think there's a lot of talent there, and we would love to bring them to the US. Some are from Dallas, some from India. Nice, nice. Cool. So, how many of you were here for the workshop last week? Okay. So some of you are here for the first time, and I want to say welcome. Saad, who is going to be hosting the workshop, is going to be joining soon, but I want him to also quickly introduce himself. And you know, before that, I'll just introduce myself briefly. So my name is Faizan. I'm the co-founder of Headstarter, and at Headstarter, we're building a lot of different things, but now we're building a platform where engineers can work on projects, get ideas of what to build next, and code and collaborate with AI to to understand their engineering abilities. So the workshop today is actually going to be taking place on our platform. So before we begin the workshop, you actually have to create an account on our website headstarter.co. I send the link in the chat. So make sure to create an account on our website, and you'll also have to get your ranks. So I think this is something that a lot of you might be kind of interested in, which is like where you rank amongst others. And so what you're gonna do is like upload your LinkedIn and your GitHub, and we're going to basically give you a score out of 100. So this score is meant to represent where you rank amongst like a senior software engineer, for example. And it also tells you a lot of interesting like metrics based on your GitHub repos as well as your career so far. So I love to see some people posting their scores in the chat. And once you get your score, you'll see I'll start sharing the screen. You see a little card in the dashboard for ML workshop series or a ML workshop code notebook. So I'll show them that. I'll show how to do that in just a bit, but Saad is joining us right now. Hey Saad, how are you?
Hey guys, how's it going? Can you guys hear me all right?
Yeah, yeah.
Okay.
Your office is full of boxes. A
Yeah,
lot of stuff.
we are going through a little bit of a move, also some spring cleaning. So yeah, that's
Nice, nice. So I think most of the people here were here for the workshop last week, but we
excellent.
do have a bunch of people who are new.
Yep.
So
That'll
I
be
would love
totally
for
fine.
you
I'll
to,
I'll give a brief couple second introduction. The
yeah,
nice thing about this series is that you can kind of think about the process of building a GPT as a bunch of concepts that you have to understand, right? You have to understand what a neural network is. You have to understand what cross-entropy law is. You have to understand what attention is. And in the next couple lectures, we are deep diving into each one of those concepts. But if you miss a class and if you miss a concept, that's okay. We are just going to basically abstract that away, right? So, for example, last time we talked about autograd and basically building a DAG system that whenever you do mathematical operations, we can take the gradient and do backpropagation. In this class, we are going to assume that, backpropagation and everything is just a given. We're not going to deep dive into, how or poke into why it works. But we're just going to use that as a building block for our next thing. So if anyone misses a lecture, no worries. You can still keep listening. You'll totally be able to understand. You just won't be able to understand some of the concepts that we build off of as deep as anything else. Do we have recordings from last lecture? Yes. Yeah.
So anything with the recording, that will be shared in an email after. So this is also being live streamed on YouTube. I mean, that's where the recording is going to be. So I would appreciate if, while the workshop is going on, you all are focused on Saad. The meeting is recorded, and so I want you all to focus on that, on Saad while the workshop is going on. But yeah, the meeting is recorded, and now that you all are going to be working on the Jupyter notebook, on our platform, it's going to be saved to your own repo. Like you get to push to your own repo as well. There's also no starting code as well. It's just like a blank Jupyter notebook. So, um, we're just going to be starting from scratch essentially. So, also, Saad, you're going to have to create an account on the Headstarter website and also get your rank. I'm very interested to see
Yeah.
where your
Yeah.
rank
I don't know if
is
it'll be
out of
very good,
100.
but for now, Fizan, I'm just going to share my screen and I'll let everyone kind of follow along.
Yeah.
But Fizan, are we good to go ahead and get started?
Yeah, so I want you to also code in the Jupyter notebook on our platform as well. So in order to do that, you'll have to
Yeah.
like calculate your rank. It's a score from 0 to 100. You just sign up on the Hashstar website, and then you just kind of follow the steps there.
Yeah.
So I'll just share it with you.
Okay, cool.
It'll just be like 1 minute takes to get it. So I set up the infrastructure to allow everyone to, run Jupyter notebooks on our platform literally yesterday. I'm hoping there's enough concurrency to support everyone. All right. So Saad is going to be working in his local machine. Um, but to simplify the process for everyone, um, because maybe you don't have the right Python configuration or something, that's why I have the online kind of version for y'all to work on. So I'm just going to share my screen real quick to show everyone where they can access the stuff. So, okay, yeah, I'm sharing my screen. So, so I myself am 86. That was my score. And once you get your score, you can just click on this link here. And what you're gonna have to do, because this is a repo that's owned by our GitHub organization, if you want to push changes to the repo, you're gonna have to first fork it. I've already forked it myself, and then now you can begin coding right here. So this works like a regular Jupyter notebook file. You can just type in the Python code here. So this is where you all can follow along.
Awesome. Fizan, let me know when we're good to get started.
Yeah, I think we should be good now.
We're good.
So
Okay,
we
perfect. I'm
can
gonna
go
share
ahead
my
and
screen
stream.
then. I got a score of 47, so I clearly have a
You
lot of
did?
work. Yes, I have a lot of work
Oh,
to do.
shoot.
Uh, uh, I have a lot of work to do on Headstarter. Hopefully, you guys can help me out. Okay, guys. Also, I just want to make a note on top. Worst case, if anything does crash on the Headstarter site, which I think is unlikely, if Fazan's an amazing engineer, but if anything does go wrong, we're starting from scratch, like literally like 0 lines of code all the way up to everything I want to write. So you can always just fire up any Python file and start running it, or your own Jupyter notebook. All right. Cool. If anyone whoever is just paying attention, if you could just drop a yes in the chat to let me know that we're good to get started. Um, yeah. Okay, perfect. Let's get into it. Okay, the nice thing about this class as well is that we have Faizan. So Faizan is going to be following alongside me, and he's going to be basically coding everything I do. And if there's anything that he finds unclear, he's going to interrupt and stop and ask me questions, as well as we have a couple people like monitoring the chat. and about logistical stuff like recording and files, and we're going to share all that stuff later. So try to keep the questions kind of focused on the content. All right, cool. Let's get into it. So if you guys remember from last lecture, we were trying to understand what a neural network is. And we basically had, this like really cool picture of a neural network that we pulled off of Google that basically tells us a neural network is a series of a bunch of layers of neurons. And each neuron basically, it's activated by some kind of input. It has neurons or inputs before it. It multiplies each of those inputs by a weight. It adds everything together and it goes ahead and fires. And if you guys remember, there was this really beautiful picture from Stanford that I really liked that was this right here, which is if we look at an individual neuron in a neural network takes inputs from previous neurons, multiplies them by those weights, adds them together, adds a bias. A bias is what we call trigger happiness in machine learning. So even if, for example, all of these weights were zero, there was no input, a bias says, how powerfully is this neuron going to fire and activate future neurons down the line? And if you guys remember, we also went over activation functions, how we applied a tanh on top of that. And once we understood this concept of a neural net, last time we basically built out micrograd. And micrograd is this like super short Python file that basically has the value class. So we can have numbers. We can multiply numbers, add them, divide them, take their exponents. And as we do this, we build up a DAG, basically a mathematical graph of all the computations. That way, when we want to determine their gradients and run backpropagation, we can basically update the weights in our neural net based off of their gradient. So that was everything we covered last time. Now we're going to kind of little bit forget about that. We're going to assume that we have access to an autograd engine. So if we want to calculate the gradients of all the mathematical operations we do, we're going to assume that's built into the library. And of course, we did that in the micrograd engine last time. So I'm going to go ahead on this totally blank Jupyter Notebook file. And again, guys, we're following Andre Karpathy's famous Zero to Hero series, so all credit is basically due to him. I'm just basically explaining a lot of the stuff that he mentions in his videos, maybe at a bit of a slower pace. Right? So today we're going to work on character level language modeling. So you guys are familiar with GPT. You guys have heard that maybe GPT is a next token predictor or a next word predictor. Basically, given a bunch of input prompts, it can predict what word comes next, then comes next, then comes next. We're going to work on a smaller level, on a character level basis. So I have this TXT file that Faizan has probably given you all access to that has like 28,000 names, right? So Ava, Azel, Baby, Bailey, whatever, all these different names. And basically, you can say that all of these names inform our model, which is going to predict more names like this. Right. So let's say, for example, you want a name that like kind of sounds legit, right? Sounds like it actually would be a name as opposed to some gibberish. Our model, which we're going to call make more, is going to predict all of these words. So let's go ahead and take this words variable. We're going to open up this file. So if we remember our file syntax in Python, we're going to read this file. We're going to split lines. That's going to place that in a Python list. And that's our word. So if I look at the first 10 words, for example, I think this list is actually sorted in terms of most frequent names. So for example, Emma or Olivia are some of those popular names. If I do some basic data analysis on this list, you'll see there's about 32,000 words in here. Let's say, okay, what's the length for each of the words? What's the length? And let's take the minimum of that. So the smallest word in this is 2 letters. So maybe something like Kai or something like that. I don't know. The maximum word in this list is 15 letters, right? So this is basically the data that we're working through. And the most basic character level model that we can make is we can say, hey, given one character, what's the most likely character to come next? Eamon, that error that you have, you just have to pip install torch. So that'll solve the problem pretty quickly. Let me just type that in the chat. Pip install torch. We're going to use PyTorch. Anyways, I'm going to keep going. So guys, have you guys ever been typing on an iPhone? And this applies for Androids too, but when you've been typing on an iPhone, you'll notice as you type, there's words that show up in that little bar that are the next word predictor. And based off of whatever word you're typing, it's going to try to predict what word comes next. Now, you'll notice if you keep spamming that over and over and over again, it's going to give you some kind of like nonsense that doesn't actually mean anything, right? We're basically building that level of word model today. This is called a bigram model. So a bigram model is a language model that takes one given input token, and based off of just one token, it predicts what's the most likely token to come next. So you can imagine if we have a list of names, a really easy way of doing that is saying, hey, let's take all of the characters in our list and let's take all the characters in our names file and ask the question, what's the most likely character to come next given an A or given a B or given a C? Right? So do you want to say that one more time? The most basic character model that we can make is we can say for all of our letters, A through Z, we can ask the question, when the letter B is present, what's the most likely character to come next? So let me go ahead and code this as a dictionary because it's sometimes easier to see that visually. So I'm going to grab, let's say just the first word, which is Emma. And I'm going to say for each of the characters in the word, I'm actually going to grab two characters at a time. You guys might have heard of the zip function in Python. So let's say, for example, I have, let's say this word right there. Oops, I have to do words. My bad. Emma is the first word. And let's say, for example, I do words, that first word, and I slice after the first letter, right? So you're going to see there's Emma and there's MMA. The zip function is really useful. It's going to basically create an iterator that is going to allow us to go element wise. So see how, for example, this is Emma and MMA. If I do a list of zip of this, you're going to see EM match with MM match with MA. And then, of course, once one of the lists no longer has anything left, once its iterator stops returning get, it's going to stop right there. So to visualize this really quickly, what this does is if I take a given word and if I shift it by one character, and then I simply just print ch1, comma ch2, see right there, we're saying, okay, for the first word, Emma, the first letter E was followed by an M. The second letter M was followed by an M. The third letter M was followed by an A, right? So things are pretty simple right there. Guys, I think a couple people are not able to find the actual file, names.txt. I'm going to just drop a link to this file in the chat just in case you guys want it. Anyways, hopefully everything makes sense. Faizan, you with me so far, right? We're basically just saying for any given
Yeah.
character, what character is going to come next, right? Obviously, I can repeat this not just for one word. I can do it for 5 words, right? So there's Emma. There's, for example, for Olivia, we have an O followed by an L followed by an I followed by a V. So I hope you guys understand that this is what we call in machine learning a bigram. These are bag of word models. In this case, our bag of words is just one token, one letter, which is the actual letter. And what we want to do is we want to basically train a model that when we have a given L, it's going to try to say, okay, I is the most likely thing to come out next, right? And it's going to make that determination by looking at all of the pairs of letters in our TXT file and basically count up, okay, how many times, for example, was a B followed by an A, or how many times was a C followed by a B, or anything like that, right? So let's go ahead and write that code. I just want to note one super quick thing. I also want to make sure that we note what the first character is. So we're going to include a very special start and end token. So let me just show you guys what that looks like. So in machine learning, usually these special tokens are enclosed by character brackets. I'm going to take the actual word that we're looking at, and we're also going to add an end token. The purpose of these tokens, you'll see, is now, just one second, instead of printing ch1, comma ch2, we're going to zip through these characters. Now you'll see right here, we have a couple extra log lines. So if I just look at that first word, Emma, previously we just had this, EM, MM, MA. We also have these 2 lines, which indicate that there's a start token that's basically saying the first token, for example, if there's nothing present, you're going to see an E right there. And once you've reached an A, you know when to end. And the purpose of this is, for example, we want to know what is the first character that basically is going to start our word and what is our last character. right? So for example, if we just polled our model that we're about to make, hey, what are the most common characters to begin with, right? That will be basically saying what are the counts of all the characters that follow the special start token. Take those counts, add them up, divide them by 26, so you get a probability, and boom, you get the probability of whatever the first token is. Fazan, you with me so far?
Yeah, I am.
Uh,
Well, so for some of the people following along, they need the names.txt. So what people can do is
I just
make
sent
a
a link in the chat. It's an
yeah, yeah.
AXT file. You can download that file. And
Just
there,
through the through like Python. This is what they can do. Just
yeah, what
request.
Fazan gave through Python is also going to do that as well. Okay, cool. If you guys just download either the file and load it onto your file system, or better yet, is just take that Python code that Fazan just pasted, then you guys will all have the names.txt. All right, is that cool? All right, perfect. Fizan, are you following along with me so far about how we have to have these special start and end tokens? That way, for example, we know, okay, what's the most likely first letter? Well, that's going to be, this pair, the start token followed by E. Or for example, what's the most likely last letter? It's going to be a given token followed by the end token. Does that make sense so far?
Give me 1 second. I gotta get this
Okay,
working.
perfect.
So people
Um,
also have to pip install requests as well.
okay. Yeah, Amen and I, you guys are with me so far, right? We're good on this start and end token. I'm gonna go a little bit slowly just to give people the chance to catch up. But I'm just gonna say this one more time. We are working on a bigram language model that's gonna take a given character and predict what's the most likely next character to come, right? We're trying to get a probability distribution of given a particular character in a name, what's the next character to show up? We have to add two special tokens, the start token and the end token, because we need to know what is our first letter even going to be, right? Because, for example, when we don't have a beginning letter to start with, we're just going to put the start token right there. And then, for example, if the model predicts end token, that's our sign to basically stop. All right, so very basic bigram model. I'm going to keep moving. If anyone is behind, then they're going to catch up quite quickly. All right, so let's actually do this for all of the words. And I actually want to store this in a dictionary called B. So what I'm going to do is I'm going to say basically a bigram is this tuple, which is ch1 maps to ch2. And I'm going to say B of bigram is going to equal b dot get. As you guys know, b dot get allows me to have a default, which is 0 in this case, that bigram plus 1, right? So that basically allows me to say that B stores all the counts. So you can see, for example, 1,531 times in this data set, E was the first letter in a given name, right? Or for example, 394 times, O was the first letter. 4,410. You guys understand what we've built basically is now I can take a look at any one of these pairs and that tells me the count of how many times that pair of characters showed up, right? Cool. Let's actually go ahead and like sort these. The easy way to do this in Python is to take b.items. B.items is going to basically give you, a tuple of basically the first tuple, which is your two characters, and of course the value itself. When you sort in Python, you want to make sure that you provide a key, and in this case, it's going to be a lambda function that basically just pulls out the second element, which in our case is the counts. Oops, we sorted naturally sorts min to max. So we have to put a negative sign right there so we can get basically, oh, now we know that the most likely bigram is that names end with an N. And the most likely name begins with an A, right? So we see that right there. Cool. Let's kind of continue on there. So you'll see we have this dictionary. It's pretty cool. If I want to search up, for example, hey, how many times, for example, do we see a C followed by an A? I'll get that, okay, 815 times, right? But I actually want to store it in a different data structure. I want to start using PyTorch. So if you guys do pip install PyTorch on your laptops, let's go ahead and import Torch. This time, I want to store it not in a dictionary. I want to store it in a 2D array. So the rows are going to represent the first character of the bigram, and the columns are going to be the second. So each entry in this 2D array is going to tell us how often the second character follows the first. But before we get to that, I just want to give a brief introduction to PyTorch again, since we kind of went a little bit fast last time. PyTorch basically allows us to get two-dimensional or whatever dimensional tensors that we want to work with. So for example, I'm going to use the zeros function, torch.0, torch.zeros with an S, and I'm going to just put 3, 5, right? So you're going to see right there, this is a tensor that has dimensions 3, 5. If I do a.dtype, that's the type of each element, and you'll notice the default is float 32, all right? In the beginning, we're just going to test out with dtype equal to int32 because we're just dealing with counts. Oh, I'm so sorry. Torch.tin32. My bad, guys. And you can see now, instead of 0 dot, these are just zeros. So these are counts. Same thing in PyTorch. It's very easy to, for example, manipulate an element of your tensor. So for example, if I do a of 1, 3, right? That is going to go the first row, which is that one, and then 0, 1, 2, 3, the third element right there. So if I increment that by 1, then if I do A again, you see, boom, that element got increased. Okay, so that's just a brief introduction to what PyTorch and tensors are. Faizan, are you with me now?
Yeah, I'm with you. I think, can you just go a bit slower just for
Yes.
some
Yes.
folks?
So again, just to start over again, we are doing bigram modeling. We have start and end tokens. Previously, I was storing everything in a dictionary. Now I'm trying to introduce the concept of storing everything in a tensor. All right, I'm going to explain that in a second. You good, Faizan?
Yeah.
Okay, cool. So I want to basically have a 28 by 28 array. Super quick question for the chat. There's 26 letters in the English alphabet. Why do you guys think my matrix has to be 28 by 28? What do I have to take account of? Space and dot, no, there are no spaces, nor are there any dots in this data set. Start and end, perfect. Everyone's got it. Start and end tokens, right? So that's going to be the extra 2 rows right there. So cool. Let's go ahead and do that. So let's say that n is equal to torch.zeros of 28, 28. It's just a square matrix. And again, we're going to keep the dtype equal to int32 because these are just counts, right? So if I'm going to show you guys this, it's just a bunch of zeros, right? Nothing crazy like there. Let me just make sure that there are actually 26 letters in the English alphabet. I kind of forget sometimes. So I'm just going to take the entire words file, join it all together, right? It's like a giant freaking thing. I'm going to put it in a set, right? Okay, that's all the letters. I'm going to put it in a list. That's all the letters. And I'm going to make it sorted. That is, let's take the length of this. Yeah, that's right. Okay, there are 26 letters in the English alphabet. Forgive me, I forget sometimes. So these are all my characters, right? So my characters, boom, right? 26 letters, easy peasy, right? I'm gonna make a really quick helper function, guys. This is gonna be called S to I. S to I is gonna be super straightforward. It's gonna be a mapping from a given character to what its index in the alphabet is. So obviously Z is gonna be 25, and as we know, ABC, 0 is the first letter, all right? And remember, guys, we need to make sure that we include a mapping for our start token, which is gonna be 27, sorry, 26, S2I, and then we're going to have our N token, which is going to be 27, right? So now we have S2I has 28 elements, and we have the indices for them right there. Cool, pretty basic so far. Awesome. Now let's go through each of our words. And let's go ahead and update the counts in our 2D array. So what we're going to do is we're going to iterate through each of the words. Remember, we're going to add to the front and to the end of the word, similar to how we did before, the start and end token, right? So remember, our start and end token is that, and that's our start token, and there's our end token right there. Cool. Now we're going to iterate through each of these characters pairwise. Remember, the way that we did pairwise is we use the zip function. We're going to take each of those characters. We're going to offset it by 1. And then, for example, if I'm going to print this, if you guys remember, this was, literally the Emma example I gave you guys last time. But now what I'm going to do is I'm going to say, okay, what's the index of this start token? The index is going to be my S2I map of that first character. What's the index of my second token? Same thing. It's going to be S2I of that second character. And now what I can do is I'm going to print instead of printing CH1 and CH. Let me just do both. Let me go ahead and print the indices as well, just so you guys can see this. So for example, the start token has an index of 26. E is the fourth letter of the alphabet. A, B, C, D, E. Remember, we are zero indexed in computer science, right? So you guys are with me so far. We're just getting indices. But the cool thing is, instead of using that stupid dictionary, which is like kind of fat and slow, we're going to store it in a 2D array, where remember, the first row is going to be indexed into what the first character is, that's IX1, and the second value, which is what column we are, is going to be indexed 2. And then we're going to go ahead and increment by 1. So that's going to take a second to run. And you'll see this is, whoopsie, I need to not just do one word, I need to do all the words. Now you'll see that took a second to run, right? It went through like 30,000 words. I have all my counts. Now you're probably thinking, I saw this is like really difficult to read, right? I know you're kind of telling me the 0th row represents A and the column represents, each of the letters that come after it. Let's come up with a little bit better way of visualizing this. I'm just going to copy paste this code in the chat. Guys, please don't worry about this at all. But this is going to allow us to visualize it. So before I do that, just 1 second. You know how I made this S to I map? It's basically, a given character to its index. I'm going to make the exact opposite. I toss. So it's going to be an integer to a string, right? So we're just going to iterate for each string, for each character, its index in that original map. And we're literally just going to reverse it. So instead of doing S comma I, it's going to be I comma S, right? Sorry, I maps to S. What you'll see right there is that just gives us, oops, I'm so sorry, guys. Um, ITOS is the flip. So it just answered the question, okay, what is the 0th element? What is the 0th letter? It's A. What is the 25th letter? It's Z. All right. Yeah, exactly. String to integer and integer to string. That's exactly right. I just needed that because it's just gonna be a little helper function going forward. I'm gonna take basically the code that I sent in the chat. Guys, really don't worry about this code. This code is just for visualization purposes. But basically, this uses Matplot, which is a visualization library. It basically makes a figure that is 28 by 28, the size of our what's it called? Array. And now you'll see it takes a second to run. Oh, it's so beautiful. It shows all of the letter pairs. Okay, so let's go ahead and
Wait,
take.
Saad, before we continue, can you just scroll up? There's a lot of code that I myself didn't
Yeah, my bad.
get.
I'm just gonna. Where did you leave off, Faizan? Did you get n
So
counts?
even the S to I function, I didn't fully get that.
Yeah, yeah, no worries. Yeah, and thank you for interrupting me. So just remember, did you get n? So n is
Yes,
basically a
that I did.
28 by 28 2D array. It's filled with ints. It's empty right now. Then what we did is we said, okay, let me grab all the characters. So characters is basically just grab every single word, get all the sets, get the list, sort it. So this is all 26 characters of the English alphabet. And then we just make a
Wait,
very,
one second. Can you
yeah, no
scroll up?
worries.
Join words. Okay.
Yeah, I'll drop that in the chat too. I know I type kind of fast. Sorry, guys. Um, and then, yeah, so those two lines will basically give you every letter in the English alphabet, and then we're going to enumerate them by their index, and then we're going to manually add, what's it called? The start and the end token with indices 26 and 27. Does that make sense, Fizan?
Yes.
Perfect. So now we have S to I, string to int. Then I went ahead and I made this little block of code, which, what's it called? Increments the counts. We have this n. And Fizan, I'm going to let you kind of copy this. And in the meanwhile, I'm just going to talk, if that's okay. So are you good, Fizan? I'm just going to yap a little bit. I,
Once printing out and okay, I see and
Quick question, what dimension is the tensor? The tensor is 28 by 28. If you remember, Jonathan, the reason it has to be that is because we're saying what's the rows represent the first character. That's the Eamon is totally right. You're filling the matrix with the occurrences of each bigram, right? So the row represents, so guys, if I go to my visualization right here, each row you'll see here, so for example, AA, this cell is telling me that 556 times in names.txt does A follow A. So you'll see this first row is all A, AB, AC, AD, AE, right? And then, for example, like any other row, as I go row wise, it changes the first character. So the second row is BA, BB, BC. So you'll see, for example, BK actually never shows up in the database. Keep that in mind. We have some zeros in this two-dimensional array. That's going to cause us problems later on. I'm going to explain that in a second. But I think the most interesting thing is there's actually an entire zero column and zero row. Can anyone point out where the zero column is in the chat? There's a column that's filled with zeros. No, not the diagonals. The diagonals all have numbers in them. ZZ does actually, let's see, I have no, ZZ actually happens 45 times. Like if someone's named like Jazz or something like that. Yes, second to last. That was exactly right. So second to last column right here. Can anyone maybe tell me why is it that this is an entirely zero? Actually, Fizan, let me ask you. Fizan, why do you think this column is all zeros?
No, no letter can come after the. Oh wait, hold on.
Other way around. No letter can come
Come
or the start
before
token.
the
The
start
whole
token.
point of the start token is that the start token we enforced as first. So it's obviously impossible for there to be a letter followed by the start token, right? So similarly, Faizan, take a guess. Why is there a row that's filled with zeros at the end?
Yeah, no letter can come after the
No
end.
letter can come after the end token. Okay, so now you're probably thinking, Saad, you're kind of stupid. You're wasting so much memory, right? There's an entire row that's like totally empty. There's an entire column that's totally empty. We know, obviously, there's not going to be any token after the end token, and there's not going to be any token before the start token. And you would be right, Faizan. So let's do a little bit of an optimization where instead of doing 28 by 28, let's do 27 by 27. So same thing, I'm going to say n is equal to torch.zeros of 27 by 27. And this time, the reason I'm doing 27 is I'm going to take the 26 letters of the English alphabet. And instead of having a special start and a special end token, I'm just going to have one special token, and it's going to be called dot. Okay. And dot can basically be our special token that if it's the first letter, it represents start. And if it's the last letter, it represents end. Right? Cool. So we're at 27 by 27. Let's make sure we keep the D type as torch.int32. We're only working with counts. And let's basically just take the exact same code that we ran above. So I'm going to copy that. Actually, you know, I'll just type it out in case anyone is a little bit slow. But you guys can copy this. I'm basically just taking all of the words, right? And then I'm putting it in a set, and then I'm putting that in a list, and then I'm putting that, what's it called? Sorted order, right? So that is all of the characters of the English language, right? And then, for example, if I do a dictionary comprehension and I use the enumerate, how do you spell enumerate? Enumerate function that allows me to do for each index, comma, the character, we will map the character to the index. So now you'll see string to int is right there. Oops, I need to have the in keyword, right? So there you go. That's my S2I. And remember, I to S is the exact opposite of this. It's instead of S colon I, it's I colon S. So for each, what's it called? S colon I in story dot items, right? Boom. So now I have ITOS, which is the reverse mapping. All right. So this is some handy dandy code that grabs me all the letters and the mappings of their indices. Cool. I actually want to do something a little bit special. Previously, I was going to have the special character be index 26. I actually want to give the special character, which is the dot character, will have index 0. So I'm actually going to offset everything by 1. The way that I do that is very simple. This index right here, I'm just going to do +1. And you'll see right there, now when I do S to I, now everything is one index. Now you guys are like so much more comfortable. Oof, Z is the 26th letter of the English alphabet. A is the first letter. Now we're one index just because I added 1. And then what I'm going to do is I'm going to say, okay, what's it called? S2I of 0, sorry, of the dot character is going to be 0. So now you'll see that is the 0th character, right? So I'm just keeping everything, this makes it much cleaner, everything on. All right, if it's here with me so far, I just did a little bit of offsetting. Is that cool?
Yeah, can we get a couple of seconds to
Yeah, write down the code. Yeah, no worries.
yeah, so the issue is Zoom doesn't actually let you copy code from the chat. Like
Ah, okay, okay.
yeah, what I've been doing, I take a screenshot and paste it to ChatGPT and I tell it to extract the
Yeah.
code.
Sure, sure. You can also type alongside me. I know I type fast, but
You type very fast.
I'll take breaks for people to. Again, guys, remember the concepts are the big thing here. You don't have to have the code, but you have to understand what I'm doing. All right. But Fizan, you understand conceptually. I've removed one of the start and end characters, and I just have a dot instead. Is that cool?
Got it, got it.
Awesome. Let's keep going. So now let's update our n counts to the array. So I'm going to say for each word, same as last time, I'm going to have my characters, but this time, instead of having, for example, like a special start token, we just called it the dot is our special one. And then we're going to have our list, which is our word. And then we're going to have, again, our special dot token. So I removed the start and end token that was present right here, and I replaced them with dots. All right. So now same thing for character one, comma character two. These are our bigrams. We use the zip function. This is the third time we're doing it, so hopefully you guys, get this by now. But basically, we're using the zip function to the same thing. I can print character one, comma character two, and you'll see, oopsie, it's dot E, E, M, M, A, and then a dot, right? So I just replaced that start and end token with a dot. All right, so very basic so far. Now what I'm going to do is similarly, I'm going to say, okay, what's the index? So that's S to I of the first character. What's the index of the second character? And then let's place in our N, our counts matrix, an update of that count. So it's going to take a second to run. You see that was kind of slow. And now one more time. Okay, a bunch of mess, right? No worries. I'm going to scroll up and just copy paste this code. Again, you guys don't need this code. It's not relevant for the project. It's just so I can show it to you guys. I'm going to adjust this to 27, 27. And you'll see right there, okay, exact same matrix, but this time you'll see the first row is dot A, dot B, dot C, dot D. So dot D represents that 1,690 times. D was the first word letter in a name. And then the last one is going to be Z dot Z, sorry, the last column, where is it? Sorry, the first, where am I looking? The first column right here, dot dot A dot B dot C dot D dot E dot F dot. That's saying that, okay, for A, 6,640 times A was the last character in a name. Is that fair, Fazan? I just replaced it with dots.
Yes.
All right, cool. Awesome. So you guys will see above, the first column is all the ending characters, the first row is all the starting characters. These are all counts. Counts are not that helpful when you're working with a probabilistic model. So let's turn these into probabilities. Can anyone give me a guess? How are we going to turn these into probabilities? Fazan, any guesses? Yes, Joshua, the
Well,
answer to your question is yes.
there's no.
Yeah, find the total and divide. Yeah, everyone in the chat is totally right, right? So let's actually just be a little bit basic because I want us to practice tensor manipulation as well. If I do n0, comma, a colon, that's going to grab the first row. So see that 0, 44, 10 right there, 0, 44, 10. And this row, this is, the 0th row, which represents, remember, if I scroll up, it's very obvious. It's what characters come first, right? Because it's like dot A, dot B, dot C, right? Awesome. Sorry, just making sure there's no questions in the chat. Yeah, we're good. Find total and divide. So that's the first row right there. Also, equivalently in PyTorch, you can also just write n of 0. It does the same thing. We're going to call the dot float function. That's going to convert these integers into floats. Obviously, we're going to need floats because we're going to divide, right? So for example, if I want to turn this first row into a probability distribution, I need to take each of these elements, sum them up, and divide them by the total. And that's going to give me the average, right? Or a probability. And remember, probabilities have two characteristics. Probabilities add up to 1, and probabilities are never negative. These are two things that we have to remember. This is basic statistics, but I'm going to write this down because these rules are so important. Probabilities add up to 1, and probabilities are never negative. Cool? All right, so let's just make sure that's the case. Let's go ahead and do n of 0. Let's do dot float. That's going to be, for example, the first row. Let's also grab, we're going to call that P. And let's just divide P by P dot sum, right? And there you go. P is going to be probabilities. As you can see, are any of these probabilities negative? Nope. And is the sum of P 1? Yes, it is, right? So this is the probability distribution for what's the first character to show up. So what that means is that 13% of the time, A was the first character to show up. And for example, 2.9% of the time, Z was the first character to show up, right? And yes, guys, you guys will get all the code after. The purpose of this is not to code alongside me. It's to understand the concepts as I tell them to you. But Faizan, are you with me so far? How we just made a probability distribution off of the first row, which is the first character in a name.
Yeah, makes sense.
Awesome. Let's keep going. Cool. So same thing. We know that the sum of all the probabilities has to sum to one. Cool. I'm just gonna use something called a generator. You guys can just grab this. You guys don't have to check this out, but this is the PyTorch documentation. A generator basically just allows you to do random numbers. It's very similar to the ran.ran library in Python. So don't worry about this. This is just some PyTorch semantics, but we're going to create a generator and I'm going to give it a manual seed. And I just made up this seed. It was like the timestamp of when I was working. So I'm just going to drop this seed in the chat just so you guys have it as well. All right. So you guys, again, if you really want to follow along, you can. It doesn't matter, right? This is just my seed. That way, all the numbers that you and I get, Faizan, are going to match. All right. So let's keep going. Let me just do seed is equal to that. Seed is equal to that. And that's my seed. That's my generator right now. We're going to use what's called a multinomial function. So first, I'm going to search up PyTorch multinomial. All right, so that's going to give me torch.multinomial. If anyone remembers from basic probability, a multinomial distribution is basically if I have a bunch of different probabilities, right? So the classic example is if I have a bag and I have different colored balls. I have red balls, green balls, blue balls, right? And if I know their probabilities, if I pull out a given ball, multinomial answers the question, what is the chance that this is going to be red or blue or green? All right, so that's a multinomial. And multinomial is really amazing in PyTorch because we can do num samples. So we can pull from that same bag of red, green, and blue balls like 100 times. And we can also do with replacement if we want to. So we can pull out a ball from the bag, check it, and then put that same bag in. Again, if you guys have ever taken a basic probability class, this is going to be very, very basic. So let's use that multinomial operator. And let's use the probability distribution that we calculated up here, which was for the first character. Let's set num samples equal to 1. I just want one, one to come out of here. And we're going to set with replacement equal to true. It doesn't matter right now because we're just doing one sample, but in the future it will matter. And again, we're going to pass the generator equal to G. All right, so if I do that, did I spell with replacement wrong? Yeah, it's not with replacement, it's replacement. My bad. Sorry, guys. You'll see I end up, let me call it dot item. Guys, super quick thing. Everything in PyTorch is in terms of tensors. So sometimes you'll end up in a case where you have like a singleton tensor right here, which is one number in a tensor. If you ever want to pull out one number in a tensor, you can just call dot item and you'll grab the item in there. All right, cool. Yeah, so Otis, it's exactly right. You guys can just listen and you can sort through this as you keep going. But Faizan, you're with me so far, right? So you'll see that, and if I remember, if I do I to S of 3, C is the character that came out of this multinomial, right? So I can keep calling this. In this case, I'll keep getting the same result because I'm using the same seed. But you can see that for this probability distribution, if we had like, a 13% chance of an A, a 4% chance of a B, a 4.8% chance of a C, a 5.2% chance of a C, etc. And if we pulled randomly from that bag of characters, in this case, we got a C. Does that make sense, Faizan?
Yep.
Cool. If I keep calling this multinomial, if I do ITOS of this, I'll keep getting different letters. And we would basically expect that I would get a lot of A's, right? Because A is the most common, right? Okay, so hopefully you guys can understand the idea of multinomial. Now what I'm going to do is I'm going to say, let's use our probability distribution. And let's keep calling our probability distribution until we can figure out all the characters. So let me explain what we're going to do. We're going to start with the starting token, which is a dot. And we're going to say, okay, hey, Mr. Multinomial, give me, based off of our probability distribution, what's the most likely character to come after our start token? And in this case, for example, it picks C. And then I'm going to say, okay, all right, for this C, what's the most likely character to come next? Okay, I don't know, H. And then after H comes A. And after A comes D. And after D comes the dot character. And now I have the name Chad, right? So let's go ahead and repeat that process and see what that looks like. I think once you guys see the code, you'll understand very clearly what's going on. So same thing. I'm going to grab, what's it called? My seed and my generator. Oh, actually, I don't need a copy. I already have it. Let me just delete this. I've got my seed and my generator. I'm going to set the first start character as 0, right? So this is really useful if you guys remember. If I do ITOS of 0, it's that start character right there. Then what I'm going to do is I'm going to have a while true loop. We're going to keep going, keep going, keep going. And we're only going to stop once this model outputs 0. Okay, so if IX equal, now you're probably thinking, Saad, this is going to break immediately. Okay, well, obviously, what we're going to do is the first thing is we're going to take our n. Our n is our counts 2D array. We are going to grab a given row. So remember, if I do n bracket 0, that's grabbing the row of all of the bigrams that start with the start character. If I do n bracket 26, that's grabbing the row of all the bigrams that start with the Z character. All right, so we're literally pulling each of these rows out. Okay, then what we're going to do is we're going to convert it to a float. That's the same thing we did up here. We're going to generate a probability distribution. The way that you generate probability distribution is you divide by your sum. And then what we're going to say is, okay, that's a probability distribution. Let me grab, based off of this probability distribution, for the current token that I'm at, what token, Mr. Multinomial Function, do you think is going to come next, right? So let's do torch.multi. And guys, I'm going to stop for questions in exactly 30 seconds, I promise. So let's use that same multinomial function based off of this probability distribution. We're going to pull just one sample. Num samples equals to 1. We're going to keep width replacement on. It doesn't really matter because we're just pulling out 1. And we're going to use my same generator so we all end up with the exact same result. Now, if I print ITOS of IX, you're going to see, boom, that's the first name that we predicted. 6Z, sexy. I have no idea what the hell that says. I promise I didn't make that up. So, okay, I guess sexy is the name that we right? Kind of funny right there. But again, conceptually, so I'm gonna pause for a second and just explain what I just did there because I think it's really cool. I started off with a start token. I generated a probability distribution for that start token. So I pulled the first row and I said, okay, these are all my counts. This is in my data set. How many times did, for example, B show up as the first character? How many times did Z show up? I normalized and that made a probability distribution. I pulled using the multinomial function to randomly pull something based off of those probabilities. And then what I did is I printed it. And the next time this while loop ran, it did it again. So once I pulled that C, now it's going to go into my probability distribution, sorry, my counts matrix. It's going to pull this row right here of C's. Hopefully you guys can see my mouse. That's C row. Again, normalize, multinomial, and say, okay, if C is the character, what's the most likely character to come next, Mr. Multinomial Function? It's E. And after E, it's X. And after X, it's Z. And after Z, it's E. And oh my God, once we reached E, the character that our multinomial function pulled out of the bag was a dot. So that was our sign to stop, right? So the name that we made is sexy. So Faizan, was anything clear? And I'm also gonna go ahead and look at the chat. Was Faizan, any questions on your end, or are you good?
No, I think this makes sense. I
Thanks.
think
Let me answer some of the questions in the chat really quickly, just because this is a really important thing. Okay, prediction models will be the next thing. Yes, prediction models are very important. How do you verify that the suggestion word is a valid word? So Jeff is not a valid word. Yes, Eamon, you're right. This is not a valid name. This name, sexy, I don't think it shows up any. I can guarantee if I search this thing up, it's not going to show up. Yeah, it's not in my data set, right? Our model is generating names from scratch on the fly. In the same way that GPT-3 generates text that it's never seen before, right? If you take a look at all the training data for GPT-3, right? The stuff that you guys prompt it with and make it create, it's never seen that before. It's just doing this. It's just doing based off of the given tokens I've seen so far, or actually in our case, a bigram model says based off of one token, what's the most likely token to come next? Okay, Saad answered the question perfectly. Saad Noman on seed is used to generate random numbers in a certain way. If we don't have a seed, since we have a seed, all of us are going to end up with the same random numbers. Remember, guys, there's no such thing as randomness. Nikolay, it doesn't recognize the most likely names. It just generates based off of the probability distribution of these characters, what names are likely to come out. Yes, it's pseudo-random. Okay, let's see, any other questions? People keep asking about the code. Guys, we're going to post the code afterwards. The code doesn't matter. The concept matters. Can it go in an infinite loop and not reach the dot token? Rafiq, great question. Yes, this can go forever. It's unlikely, though. The probability will just lend itself that at some point we're going to stop. All right. Okay. Anyone else? Is it like the most likely names that are not in the list already? No, Shafiq, these are not the most likely names not in the list already. This is the probability distribution of the characters, randomly sampling from that probability distribution what names come out, right? Okay, so Joshua asks an amazing question. Why is it that this E was followed by an X and this E was followed by a dot? If we were not using multinomial, if we were simply calling max on this probability function, for example, the maximum probability here is that A, the most number of names begin with an A. 13% of names begin with an A, right? If we only did max probability, then every single time we would always only have A-based names. Does that make sense? Because if we only do max probability, the answer is only going to be 1. But that's why we use the multinomial function. We want to make sure that we're not just saying, okay, what's the most likely thing to come next based off of what we've seen? If we did that, we would only ever generate one new name. What we want to do instead is we want to pull randomly from a probability distribution because that allows us to get many different variations of name. Joshua, does that make sense? Zub says makes sense. If we use a different data set, will we get different results because it's based on probabilities from a file? Yes, that's correct. Joshua, did I answer your question? Yes, no? Are there any probability distributions that would do something else more different? Yes, there are, and we're going to talk about them in just a second. I can tweak this probability distribution and yeah, we'll get there in a second. I want to do this a couple times. So I'm going to grab, you guys can keep following along if you want. I'm going to grab this seed. I'm going to actually just modify all this code. So basically, we are going to just slap a for loop on here. And we're going to run this actually 20 times. And 20 times, I'm going to, I don't want to print each character. That's going to be like super ugly to read. I'm going to have a list called my out list. And basically every time I generate a new index, I'm going to do out.append of itos, integer to string, of the index. And then I'm just going to go ahead and call print on joining each of those characters. So now you'll see these are the names that I came up with. Okay, these are pretty terrible. Sexy is the first one. Moma Sorel Ezetin, Koni Metain, Lilane, Ka Da Ki Teda. They kind of look like names, but they kind of suck. So obviously this is really bad. The reason these samples are so bad is because bigram language models are inherently terrible. They only look at two characters. So for example, when we're doing ka and da, obviously there's a bunch of names that begin with ka. Caitlin, Katie, I don't know, whatever, right? DA, David, stuff like that, right? But the problem is that once we reach this one character, the model has no context. It has no context, you might have heard that word before, to know that actually there's only, this character, we're only 2 letters in. We shouldn't stop because we've only outputted 2 letters. We should keep going because usually, names are about 5 to 6 characters in length, right? So this is bad. But I want to prove to you that this is not terrible. Like this is, I agree, these are kind of like gibberish names. But I want to prove to you this is not complete nonsense. The way I'm going to prove that to you is I'm going to take this code and I'm going to copy it. And instead of using the probability distributions from our data, I'm going to use a function called torch.ones. So torch.ones, let's do torch.ones of 27. It makes a tensor that has 27 ones. And if I do torch.ones divided by 27, I get what's called the uniform distribution. The uniform distribution says, let's say, for example, I pull from a bag that has a bunch of balls in it, and there's 3 red balls and 3 blue balls and 3 green balls, right? That's the uniform distribution. Anything that I pull, it's equally likely that I could have pulled anything else, right? So I'm going to prove to you that what we're generating is not utter nonsense by replacing this probability distribution with torch.ones divided by 27. So I'm going to do P is equal to torch.ones. P is equal to P over P dot sum. We know P dot sum is 27, but I'm just keeping the same code format. And now, okay, now you guys have to bear with me. The names are worse, right? So it is the case that when we made a probability distribution based off of our input training data, we actually got slightly better results. Like, there's no way in hell that someone would be named X66Q Citivu. It doesn't make any sense. This is actual gibberish. But this at least has a little bit of structure. You can notice that consonants are separated by vowels. You'll notice that we don't go on for too long. You'll notice that L's are followed by A's and that kind of stuff, right? So Maharshi answers the question, how are we going to fine tune this gibberish into real names? We're going to do it, but we're not going to do it today, right? Lauren says about the strange names, you should ask Elon Musk's kids. Yes, that's right. Maybe we accidentally made a model that predicts Elon's kids' names, right? So maybe you want to put that on your resume. But Faizan, are you with me so far? You see how this is an improvement? The uniform distribution is obviously worse, right?
Yeah, this is
Yeah.
yeah, makes
Now,
sense.
it's not great. It's still pretty bad. Can someone think of a basic optimization that would change it from a bigram model to what's called an n-gram model that would obviously improve our names? Can anyone drop in the chat? Fizan, any ideas too? What do you think will be so obviously that would fix this problem?
Yeah, I mean, so based on the n number of uh letters that are current, you get the probability of the next letter after that.
Exactly. Saad gave the exact answer in the chat. Instead of using a given character to predict the next character, we should group words at a time. So instead of saying, okay, given that there's an A, what's the most likely thing to come next? We should say, given that there's, for example, an FA, fa, what letter comes next? Or if we, for example, do 3 groups of words or 4 groups of words, this is called adding context to our model. Now, today we have a very different word for context. Context is used in the world of like AI agents and context engineering and all that kind of stuff. But this is where the original context came from. Right now, our context is 1 character deep. If we were to, for example, have not a bigram model, but a trigram model, we would have 3 characters, so like 2 then 1. So it'd be 2 characters that we have as input and 1 character that comes out. Does that make sense? How we can increase our context and maybe we'll get better results that way. Is that fair?
Makes sense.
Okay,
Yeah.
well, guess what, guys? We're not doing that today. Screw
Mhm.
that. We're going to do that next lecture. That's too much work. We're going to actually go in a different direction. The reason is if you guys tried implementing a trigram or a quadgram or a pentagram or whatever the hell, an n-gram or even an attention model that attends to all the tokens in parallel, that's how GPT works, you would basically go crazy. Like the amount of code that it would take based off of our current architecture using a 2D array, it's just not possible. You're going to end up with these like really ugly looking 3D arrays, 4D arrays. It's just not efficient. So instead, how about we train a neural network that does the exact same thing? And if we can train a neural network that can work off of 1 token, it's so trivial to change that neural network to work on multiple tokens. All right, is that cool? Let's get some neural networks up in this game. Okay, before I do, I actually want to do a slight improvement. So you'll notice there's actually something that's like making this like really slow. And that's if I go to, I'm going to delete this code right here, delete this. This is the one that I liked, right? It came up with the name sexy. You'll notice we're calculating probabilities over and over and over and over again. That's the reason why this function is so freaking slow, right? Well, I only excuse me, I only ran it 20 times. If I run it 200 times, it's gonna be super slow, right? It's actually not that efficient. And the reason is you guys notice this code is getting run over and over and over again. We're over and over and over again. We're pulling out from our 2D array. We're grabbing the counts. We're taking the sum and we're dividing. So obviously what we should do is instead of, just having a counts array, we should have a probability array. Now you might think, Saad, this is not that big of a deal. The thing is still pretty fast. Screw it. I want us to practice playing around with PyTorch and manipulating tensors. Because if you get good at manipulating tensors, you are going to be hired as a machine learning engineer. I can promise you that. Cool. Let's work on that. So let's say that P is equal to n dot float. And that just makes a copy. That's all, floats. And let's take P dot sum really quickly. Oh, shoot. I wanted to take my 2D array and take all the counts, and I want to divide not by the total sum of the 2D array, but I want to divide for each row's sum, right? So for example, for the first one, for the this row over here, I want to divide by its row's sum. For the second row, I want to divide by its row's sum. Third one, I want to divide by its row's sum. So when I do this, previously I was going to do n dot float, and I was going to do, p is equal to p divided by p dot sum. This is actually wrong. And the reason is that p dot sum is not, what's it called? P is equal to n dot float. P dot sum. This is the sum of every single count in the 2D array, right? So Fizan, does that make sense? I want to get a row-wise sum. I don't want to get a sum of every single count in my 2D array. What p dot sum is doing is taking every single freaking number in here, all 28 times 28 numbers, and adding them up. I don't want that. I want to be able to divide each element by the sum of the row that it's in. This is called a row-wise sum. So we're going to have to learn a little bit about the torch.sum function. Okay, the documentation is very straightforward. It takes in an input and it takes in a dimension. If you don't specify a dimension, it will sum everything together. Exactly as we saw that, this n dot float, it basically got collapsed into a single unit tensor, right? Josh was asking, would there ever be a need for a column-wise sum? No, not yet, but we're going to get there in a second. Let's first practice working with torch.sum. So let's practice working with tensors. And again, guys, you don't have to follow along exactly, but Faizan is, so I'm going to torture him a little bit by making code. Okay, Faizan, we're making a tensor that is 2 by 3, and it's 1, 2, 3, 4, 5, 6. Is that cool? Are you with me so far?
Yeah.
Okay, I'm going to do x dot shape. You can see, oops, I need to, what did I do? Oh, I have to put brackets right here. Sorry, guys. There we go. So, it's a proper matrix. The shape of this tensor is 2 by 3. All right. Duh, obviously. Let's practice some sums. So if I do torch dot sum of x, it's going to do 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. That's not what I want. I want the column-wise sum. So if we if we set dimension equal to 0, that's going to sum down the rows, which is also known as the column-wise sum. So let me prove that to you. If I do torch.sum of dim equals 0, I'm going to end up with 5, 7, and 9. And you see how, Fazan, that's exactly the column-wise sum. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9, right? Let's change this. And now let's do dim equals 1. Let's now sum across the columns, and let's get what we wanted before, the row-wise sum. So you'll see 1 plus 2 plus 3 is in fact 6, and 4 plus 5 plus 6 is in fact 15. All right, so now we have the row-wise sum. I just want to make sure of just one click thing. What's kind of annoying is the shape of this vector is pretty terrible. Let me just show you that real fast. So if I'm going to print the shape as well, the shape is 2, or at least 2 comma 1, right? But this is a row vector right now. I actually want 1 comma 2. I'm going to show you guys that why in a second. But if I'm doing a row-wise sum, I want to have basically a column vector where every entry is the sum of each row. That way, I'm going to do what's called a broadcast operation, and I'm going to divide my matrix by that column, and it's going to give me the proper answer. So I need to use something called keep dims. So you'll see over here, keep dim. If keep dim is true, the output tensor is of the same size as input, except one of the dimensions are squeezed out. So let me show you what that looks like. If I do torch dot sum of x comma dim equals 1, you'll see that's just 6 by 615, right? That's a row vector. But if I do torch dot sum x dim equals 1, and now I do keep dim equals true, Fizan, do you see the difference? What's the difference right there? How is this different?
There's two rows.
Yeah, this is a
Yeah.
column vector, right? This, see over here, this was 2 by 1, right? Agreed? This over here, this is, or I guess in this case, it's actually 1 by 2, but it depends on whatever your notation is. This is basically the point I'm trying to get you to say this is a row vector, right? This thing is actually a column vector, right? Because this actually has a shape of 2 by 1. Right? So that's the point of keep dim. It's just very important to just understand how these broadcasts work. I'm just going into a lot of depth here because I want us to really get comfortable with PyTorch because going forward, we're going to use it like crazy. Awesome. I'm going to take this tensor right here, which is keep dim, and I'm basically going to do the exact same thing, but now I'm going to do with n. So remember, if I grab n, that's my counts matrix. I'm going to do n dot float. I want everything to be in floats. Now I'm going to retorch.sum. And if I do dim equals 1, I'm going to end up with a row vector. But remember, guys, I want a column vector because what I want to do is I want to take each of my rows and I want to divide each row by one of the entries in the column. All right, so I'm going to do keep dim equals true. There you go. That's my column vector. If I give you the shape, you'll realize, okay, yeah, it is 27 by 1. Okay, so why is this so important? The reason this is important is now what I can do is I can divide my counts matrix, which is n, by this right here. And whenever we manipulate or divide these kind of matrices or vectors together, we have to keep in mind what's called broadcasting rules. Okay, so really quickly, this is the sum. Let me just do, sorry, just one second. I'm going to do P is equal to n dot float. I'm going to divide by this expression that I got right here. And now you'll see I actually have the correct probability distribution. And how will I prove that to you? Well, if I do P of 0, that's the first row. If I sum it, boom, the sum is 1, right? And just to be sure, just as a sanity check, if I grab, for example, let's say the first column, the sum is not 1, right? So the rows right now are summing up to 1, right? The columns are not summing up to 1. Does that make sense for them?
Uh, Sorry, I was just having the code. Can you repeat it one more time?
Let me say this one more time. I have my counts matrix n. I'm going to divide by a column where each column has the sum, right? So each row, the first row is going to get divided by 32,000. The second row is going to get divided by 33,000. These are my row-wise sums. Now I generated my probability distribution, and I know this is a valid probability distribution because if I look at each row, nothing is negative, and the sum is 1. Does that make sense? How I made a probability matrix?
Yeah, got it.
Okay. I want to talk about that division was kind of finicky. How the hell did I have a 27 by 27 matrix? This is n. And how the heck can you divide 27 by 27 by 1? Because remember, this thing right here, this sum that we did, its shape is 27 by 1. So any guesses? What the hell is going on here? How can you take a 27 by 27 tensor and divide it by 27 by 1? The shapes are mismatched. The answer is what's called torch broadcasting semantics. So I'm going to drop those links in the chat. I find this really interesting. The reason this is very interesting is because when you train machine learning models on multiple GPUs, you have to like manipulate tensors, chop them up, divvy them up, do matrix multiplication. And it's really important to know how are these dimensions being treated? Right now, I'm giving you a very basic example, right? Obviously, everybody knows that you can divide this because it's going to make copies. And I'm going to show you that in a second. But this is going to be your cheat sheet when you become a machine learning engineer. Okay, we're going to use this later when we what's it called? Do the next GPT lecture. But I'm just gonna put that link right there. I want to just show you what actually happens. So if I have a 27 by 27 matrix and I want to divide it by 27 comma 1, what happens is that internally PyTorch is going to take that 27 by 1 column vector and it's going to make 27 copies. That way it can multiply out, it can, sorry, divide element wise. So this 27 by 1, it's going to do what's called broadcasting, and it's going to turn our 27 by 1 into a 27 by 27. So now once it takes that column and concats it 27 times, makes 27 copies of it, now we can divide element wise. Does that make sense, Faizan, what's going on here? Again, it's a very basic division, but I'm explaining it in detail so we know what's going on under the hood.
Got it.
That makes sense. Okay, cool. And let's see if are there any questions. Everyone in the chat seems pretty good. Yes, for the millionth time, we will definitely have recordings and the code. Don't worry about logistical stuff, guys. You guys can ask that at the end. Okay, awesome. Let's go ahead and take our code from above, copy, paste. And now, instead of using this ugly thing that recalculates the probability thing every single time, we're just going to say that our probability distribution is simply equal to the big P, capital P, that's our probability matrix, and then the actual index. And you'll see we get the exact same names, right? Sexy is our first name, right? So I'm just replacing those two lines up here instead of, I gave you such a long lecture, just to teach us about how to manipulate, how to sum, how to broadcast these PyTorch tensors. It's very important to learn that. Okay, cool. I want to show you guys just one thing. Okay. I want to show you guys something really quickly. Just one second. You guys notice that I use this keepdim function. I'm hammering this over and over again. What would happen if I set it to false? Do we think this would work? Well, the math obviously works. What we have over here is we have a 27 by 27 matrix. And in this case, we have a row vector, which is just 27. So according to the broadcast rules, this does work. And you can go into broadcast rules in a second. But basically, if we stack all the dimensions right aligned, if the dimensions are the same, no problem. And if there isn't dimension, we ignore it. That's the broadcasting rules. Now, this does actually work. You'll see if I turn keep dim equal to false, that did work. But if I take the same code, you'll notice the names are kind of different. So what the hell? What happened here? There was an error. There's a very hidden bug. And guys, this is why I'm telling you this right now, because I'm telling you, when you guys become ML engineers, you guys are going to find these like really difficult to spot bugs where if you turn even a single flag off, your output is going to look totally different. So what went wrong here? It's really hard to tell, but the way that broadcasting semantics works is that it takes the dimensions. In this case, n is 27 by 27, and our p dot sum, when we didn't use keep dim, is a row vector. So it's 1 by 27. It checks, are these two entries the same? If they are, move on. And now it's going to say, okay, 1 and 27, these are not the same. So I'm going to multiply out, and I'm going to take my one row vector, and I'm going to make 27 copies, 27 rows that are the same. Boom, that's our bug. Torch previously, when we did keep dim equals true, it took one column and it made 27 copies. Now what's happened is because we didn't set keep dim, we accidentally made our sum vector a row vector and made 27 rows that are stacked on top of each other. I know it might be a little confusing, but the point is, if I take this new P and I sum the first row, oh my God, this is no longer a probability distribution because it doesn't sum to 1. So accidentally what we did is instead of normalizing the rows, we normalized the columns. If I take a given column, now that sums to 1. Sorry, guys, I can't visualize this, but is everyone with me so far on how just one flag, you need to make sure that your broadcasting semantics are right. So you want to make sure that when you normalize a matrix, you want to make sure that you divide, in this case, by the row-wise sum. All right, cool. If that all went over your head, no worries. Let's completely move on. Fizan, are you good?
Yep.
Okay, cool. Let's keep going. Let's take a look at some of the probabilities that the model assigned to each of these bigrams. Let's look at some probabilities, okay? So for example, what I'm going to do is I'm going to copy the code that I had previously. I'm going to grab the first three words. Same thing. I'm going to have these dots. Actually, hold on just one second. Sorry, one second, guys. Just 1 second. Okay, I'm just going to copy this code right here. This is a copy of what we had done previously up above. I'm just going to grab that down here. So this is the code that basically takes .em whatever. Actually, let me not print this yet. So this is the previous code that we had, right? It just prints out in our data set what are the orders of the words, right? Fizan, do you see this?
Yes.
Yeah, okay, so this is just the ordering of the characters. I'm going to add the probability. So the probability is we take our P matrix and we index into it based off of the first and second character. And now let's print out those probabilities. So what do these probabilities mean? These probabilities are saying that for each of these pairings that we're seeing, 7% of the time in the total data set, we saw M and then an A, right? And I want you guys to remember that the uniform distribution, which was the garbage gobbledygook that we made previously, that was where basically all of these were just set to 1 over 27, right? So that was every single bigram had a probability of showing up 3.7% of times. So what I want to make sure is that whenever we're looking at our training data and whenever we're trying to predict the data that we've already seen, right? Like for example, Emma, we want all of these probabilities to be very high, right? We know that Emma is in the data set. Whenever, for example, we have EM, we should make sure that this is a very high probability. We've obviously seen it before, right? So you can see right here, 11% is certainly bigger than this 3.4. So anything above the uniform distribution is useful. You want to make sure that our model, which took a probability distribution of the names.txt file, whenever we run it on those same names, it gets very high probabilities. Does that make sense, Faizan?
Yes.
Okay, perfect. This is called fitting your training data. Our training data is a bunch of names, and we want to make sure that our model can not just predict new names, but it does a good job on the training data of names that we already have. So if we give our model EMM, we really want it to predict A after that, because that word shows up in the training data. So I want you guys to now say, okay, how can we make sure that our model, our probability distribution is as high as possible? So Maharsi is asking, how do we increase probability? Should we more than uniform distribution? I'm going to talk about that in a second. We can do different things. You know, we can have different types of models, maybe trigram models, maybe quadgram models that are going to fit the data distribution a little bit better. But for now, I just want to understand mathematically, how do we know if our model is even doing a good job? Right? Like I told you guys that bigram is a pretty bad model, but trigram, if you look at 2 characters at a time, or quadgram, if you look at 3, or pentagram is a better. What's a statistic that I can tell you that will tell you with 100% confidence, okay, this model is better than another model? And this is where we go to our statistics classes and we search up maximum likelihood estimation. So maximum likelihood estimation, this comes from the concept of likelihood. So in probability, a likelihood is the multiplication of multiple probabilities. For example, if I just take the word Emma, right? The likelihood that our model would predict Emma is this first probability. Remember, 7.5% of the time, our multinomial function is going to pull out an E. And then once we grab that E, 11% of the time after that, we're going to grab an M. And then 2% of the time after that, we're going to grab another M. And 7% after that, we're going to grab an A. And 20% after that, we're going to end. So Faizan, do you see how probabilities are multiplicative? If you wanted to answer the question, what's the likelihood that our model would predict the word Emma, you would take the probabilities that our model assigned to each of the bigrams and you would multiply them. So you would do 0.75 times 0.1158 times 0.0253, 0.764, 0.2073. This is the likelihood. Oh my God, that's a super small number. It's like 3 millionths of a percent or whatever that we would actually predict the word Emma. Does that make sense, Fazan, where I pulled this statistic out of?
Yes.
Okay. So again, I'm going to say this because this is, I will be very clear. Some of us maybe have forgotten our basic statistics. Likelihood is we're saying what's the chance that our model predicts the word Emma? And our model predicts the first character E 7.5% of the time. If you take of that 7.5% of the time, we will then predict an M. And of that 11% of 7%, we will predict another M. And of that 7% of 11% of 2.5% of 7.6% of 2%, we will predict the whole word Emma. So the nice thing is probabilities are multiplicative. The model that we have generated will predict the word Emma 3 millionths of a percent, right? So not great, right? We want a probability, we want a likelihood that is as near 1.0 as possible. Again, this is what's called fitting the training data. If we can't even predict the names in our own data set, this is a pretty garbage model, right? So one last time, we want to make sure that we maximize the likelihood of predicting the words in your data set. This is called maximum likelihood, I spelled likelihood wrong, estimation, or MLE, right? This is a statistics concept. You can read about it more. So we want that to be as close to 1.0 as possible. All right. Awesome. Let me move on then. Now, how can we get this up to 1.0? That's probably what you guys are asking. We're going to work on different model techniques in the next couple lectures on getting that up. But I want you guys to understand the statistic that tells us if we're doing a good job is likelihood. All right, maximum likelihood. Now, working with probabilities is a mess. When you multiply these probabilities, you guys might have noticed we're getting these like really, really tiny numbers. So yeah, I want us to maximize the likelihood, be as close to 1.0 as possible. But just like, logistically, when I'm like working with these numbers, these are such small numbers. My computer is going to end up with all these errors. You guys can hopefully see multiplying probabilities is a bad idea. So if I can't multiply probabilities, what if I slap a logarithm? Eamon has predicted what I'm going to say. We know from basic maths that log of A times B times C is equal to log of A plus log of B plus log of C. Now, you guys don't have to write down this. I just want to show you this. This is the logarithm function. You can see, let me just open Desmos. That's more fun. Log of X is a function that's monotonically increasing. That means it always, always increases. So that means if I want to maximize a function X, it's equivalent to maximize log of X. If I maximize log of X, I'm definitely maximizing X. And that's because it's a monotonically increasing function. All right. You can see log of X has a couple nice properties. It's, it's not constricted. It ranges from negative infinity all the way up to infinity. And of course, we have to start at 0. So usually for convenience, ML researchers don't like to work with likelihood because you have to multiply and end up with these super small probabilities. They work with log likelihood. Log likelihood is where we are now able to add up these numbers because we are working with logarithms, right? So one more time, you'll see that for numbers near 0, we're going to tend towards negative infinity. Okay, cool. So we want to make a model that will maximize the likelihood that we estimate the data in our own data set. And we said, okay, maximizing likelihood was like really freaking annoying. So you know what? Let's maximize log likelihood. All right, log likelihood. Now, guys, remember, probabilities range from 0 to 1. So if I look at this function, log of X from 0 Up until 1, you guys will notice that it is all negative. Log of x is always negative between 0 to 1. This is kind of annoying. In machine learning, we prefer not to deal with negative numbers. So instead of maximizing the log likelihood, let's minimize the negative log likelihood. Again, I'm going to step back for a second. The reason I'm spelling this out is I want to know what's the best type of model. The best type of model is the model that maximizes the likelihood. Maximizing likelihood is the same thing as maximizing the log likelihood. Maximizing the log likelihood is the same thing as minimizing the negative log likelihood. Fazan, are you with me?
Yeah.
Awesome. Cool. We're going deep into statistics, but I think it's really important here. The final thing that I'm just going to say, and you just have to trust me, minimizing the negative log likelihood for a data set, what does that look like? That looks like minimizing the average negative log likelihood across all data. So what we're going to do is, again, previously with just Emma, yeah, you're right. We wanted to get Emma all the way up to 100% likelihood, right? Or in this case, we want to get it as close to 0 as we can because we're minimizing, right? But again, we don't just have the word Emma in our, what's it called? A data set. We have all these different words. So we want to make sure that the log likelihood across all of these words, the average is the average is as low as possible. Cool. So our goal is we want to construct a model, be it bigram, be it GPT-3, be it GPT-5. Every freaking model in the world works the same way, where they're trying to maximize the likelihood, which is all equivalent to the end of the day, minimizing the negative log likelihood, but averaged across all the data. All right, cool. Yes, log of average will be greater than 1. Ganesh asks, what's the point of negating it? When we negated it, we flipped from maximize to minimize. Ganesh, there's no real point in this other than machine learning researchers like to be consistent, and they never use the word max. They always keep everything in terms of mins. That's because they use words like loss, and traditionally in English, you want to think that you're minimizing the loss, not that you're maximizing the negative loss, right? So again, our loss function for this model, remember last time, guys, a loss function is a statistic that tells you how good is my model. Our loss function is the average negative log likelihood. This is going to relate exactly to cross entropy loss in a second. I'm not going to get into that today, but let's go ahead and calculate for, let's say, 3 words. Let's go ahead and do the same thing. Let's append the start token to the start and the end token to the word. Let's do the same thing. This is like the 10th time I'm doing this by now, where I'm going to iterate through basically the bigram of the characters by shifting by 1 right here. So I'm going to iterate through basically all the possible things. You guys can remember if I print CH1 and CH2 here, I get Emma, Olivia, and Ava, right? And I see their bigrams. But now what I want to do is, instead of just printing, I want to grab their indices. So that's S2I. Oh, sorry, I want to grab the actual indices. So it's S2I of CH1. Index 2 is S2I of CH2. So now, of course, if I print this, I'm not going to get characters. I'm going to get numbers. And now what I want to do is I want to go to my probability matrix. I want to grab what's the probability for each of these bigrams. That's going to be prob. Now let's go ahead and print that. So I'm just going to use a little bit of fancy schmancy, what's it called? String parsing right here. So I'm going to do character 1, character 2, colon. The probabilities, guys, are really ugly, and they're going to show up let me do 4 decimal places. Okay, so if I print that, oh, Jesus, what did I do? Put a close quote right there. Okay, so now you'll see exactly as I did before, 7.5, 7.5, right? I'm getting the probability that our model assigns to each of these bigrams. But now I don't want to just do probability. I want to do log probability, right? So I'm going to do torch.log of the probability. And then I want to do what's it called? The log likelihood, right? And the likelihood is going to be basically, remember, previously we were multiplying likelihoods, but now because I slapped a logarithm on it, I can just add these. Easy peasy, lemon squeezy, right? So log likelihood is basically adding up all these log probabilities. And now I'm going to now print both the probability. I also want to show you guys the log probability. And at the end, I'm going to print for you the final log likelihood, which is the statistic that tells me how good or bad my model is. This is called a loss function in machine learning. And boom, there we go. You guys should get the same number. So my function is -38 bad. Okay. So remember, if I was perfect, let's say, for example, I had 100% probability, right? Log of 1.0. Let's see, what's log of 1.0? Oh, it's 0. Okay. So log of 1.0 is 0. So if I was doing perfectly, I would have 0 as my log probability, and my log likelihood would be zeros all the way across. So basically, log likelihood can be 0 maximum. Or, for example, or if my model is bad, it can be more and more negative, right? So, for example, we'll see over here, I predicted 7.5%, which is pretty terrible. So I got a -2.5 log probability, and I added up all these penalties, and I got a loss of -40. So you guys see, 0 is the best that I can do in terms of log likelihood. That's where I get 1.0 probabilities for everything. Log of 1.0 is 0. Sum up all those zeros and I end up with 0. And then, of course, it can go as terribly negative. Okay? And remember, guys, we don't like this in machine learning. We prefer not to work with like we don't want like have this like weird negativeness going on. So instead, I'm going to print out not just a log likelihood, I'm going to print out the negative log likelihood, right? That's what I told you. That's what I promised to you guys before. So that's negative 1 times log likelihood, right? So boom, there we go. So now, okay, things make so much sense. My loss function is negative log likelihood. When my loss is higher, right? That's going to be a higher number right here. That means I'm doing worse. And the best that I can do is a loss of 0, right? Or my model is perfectly predicting everything. If I perfectly predict everything, every probability is going to be a 1. Log of 1 is 0. Sum up all those zeros, and boom, there you go. My loss is 0. So Faizan, do you understand how I just constructed for us a loss function that tells me how good or bad my model is?
Yes.
Okay, cool. I'm going to move on. And now, remember, I don't want to just do it for one word, right? This is actually just giving it, like, this was what we, this is for one word, for the word Olivia. Sorry, for the word Emma. I want to average it across all of my words. So what I'm going to do is I'm going to also increment a counter. And then I'm going to take the negative log likelihood and I'm actually going to divide it. I'm going to say my mean negative log likelihood. That's my log likelihood divided by my total number of samples. In this case, in this data set, let's do 10 samples. Uh, so divided by n. So now you'll see there's my mean negative log likelihood. You want to make sure that, for example, just because you have more data, you're not getting a higher loss function, right? You want to average. What's the average negative log likelihood? Okay, cool. So now we know that we are minimizing the mean negative log likelihood. That's the goal. Make a, what's it called? Make a model that is able to minimize mean negative log likelihood, and boom, we will end up with beautifully flowing words. Right now, we're pretty terrible. We have an average loss of 2.4. 2.4 is actually, it's not terrible. If we, for example, if we change this to be, actually, let me show you. This will be really interesting. Let's try to figure out what would the loss function be if instead of using our probability thing, we did torch dot ones of 27 divided by 27. Oopsie doopsie. What should I do? Prob. Sorry, just one sec, guys. Uh, oh, this has to be, this is basically just 1 over 27, right? So the probability, if it was always 1 over 27, this needs to be a torch. Sorry, guys. Torch.tensor. See. Okay, there we go. So 1 over 27 is 3.7%. If it's always 3.7%, I end up with a really bad loss, 3.3, right? So the loss that I'm achieving right now, so now I've proved to you mathematically, not just by showing you the difference between the words, but see how over here I'm predicting sexy and, lan and ka and da. Mathematically, I'm showing you that actually I am better. Previously, if I just use the uniform distribution, I have a loss of 3.3. But if I use the distribution based off of the data, I achieve a better loss. So now my goal is to get you guys in the last 20 minutes, and this is going to be super fast. You guys are going to love it. We're going to train a neural network that's going to achieve a similar loss. Fizan, you understand everything about the statistics and everything so far? Any questions so far? No, I feel like I tried to purposely go slow, but hopefully everything was good there.
I think I'm good.
You're good?
Any questions in the chat?
Okay. Um, awesome. I want to show you guys just one more thing. Do you guys remember how I said that in this 2D array, there's some zeros? Does anyone know what log of zero is? Anyone know what log of zero is? Nope, not one. Log of zero is negative infinity. So if I ever have a probability of zero probability of predicting a bigram, I'm screwed because I'm going to introduce a bunch of infinities into my data set. So let me show you what that looks like. Let's say, for example, I have the word Andrei Karpathy in honor of him, right? So in this word, the loss is, oops, actually, this is the wrong cell. Let me not do this one. Let me do this one right here. Let's do it right here. Let me comment out that. And let's do for each W in Andre, right? In honor of Andre Karpathy. You'll see that I achieve a loss of 3, right? You'll see that the model's, it's not the best. Let's say, for example, the name was Andre Q. You'll notice that everything explodes to infinity. Why is that? Because you see, if I go to my count, JQ shows up 0 times. So then when I calculate the probability, I end up with 0. The log probability is negative infinity. And then the negative log likelihood. So then obviously the likelihood is multiplying all of these, or sorry, in this case, it's adding everything. So -2 plus -1 plus negative infinity is obviously negative infinity. So I end up with this like stupidly like terrible loss. So how do I fix this problem? This is a problem that machine learning researchers end up to all the time. So you'll notice when you're an ML researcher, there's two things you hate, inf and nans. So you'll frequently see as you're training, your loss function will either explode and become nan, which means not a number or infinity, and that's exactly what's happening here. So hopefully you guys understand mathematically, when we have a count of 0 and a probability of 0, when we take the log of 0, everything goes wrong. So how do we solve this problem? Easy peasy lemon squeezy. ML researchers do something called smoothing. So let's smooth our model. How are we going to smooth our model? We can smooth our model by taking that same probability distribution. And previously, what we were doing is we were taking all the counts. These are all the counts. And some of them were, in fact, 0, right? So now what we're going to do is we're just going to add. So let me just grab this right here. So you'll see some of these entries are, in fact, 0. What I can do is what's called smoothing the function. What that means is I'm going to add 1 to every single count. So worst case, yeah, I know I kind of like manipulated this data, but I'm going to put just 1. That way, when we do our probabilities, we never end up with any 0 probabilities. And that way, when we do our log probabilities, instead of ending up with a 0, a log of 0 is infinity, we're going to end up with a super small number, and that's going to represent basically nothing. Now, guys, you can imagine if I didn't do p is equal to n plus 1, but if I did p is equal to n plus a gajillion, effectively what I'm doing is I'm squishing the probability distribution together, right? So previously we had a spike, let's say. We know that A is the most likely first letter, right? So we have a spike when it comes to A. But if, for example, I add, I don't know, a gajillion, then the relative difference between how many times A is showing up versus any other number is showing up, that gets flattened out. And then we're basically back at the uniform distribution. So this is what's called smoothing in machine learning. If ever you have a problem where you have 0 probabilities, smooth your model and you won't run into this. Let me just prove to you that this solves the problem. So if I do p is equal to n plus 1, those are my counts. And remember, I'm going to turn this into float. And then I'm going to say p is equal to p divided by p dot sum. and we have to set keep dim is equal to true. I went on a whole tangent explaining that. And now if I run it for Andre, you can see, sorry, for Andre Q. Previously, we had a negative infinity error. And now I solved that problem because when we get to JQ, the probability is not going to be 0. It's going to be really, really small. Does that make sense, Faizan? How I artificially kind of messed up the data in order to make sure I don't have any infinity problems. Is that cool? Faizan?
Yeah,
Yeah,
makes sense.
awesome. Awesome. Now we're going to do the exciting part, which is you guys are probably thinking, oh my God, Saad, how are you going to do this so quickly? Let's make some neural networks. Okay. I'm going to go a little bit faster here. I'm sorry, guys, we're just running short on time, but it's going to make a lot of sense. Let's make the training data set. So let's have our X's. So in machine learning, we have X's and we have Y's. These are going to be two lists. Then we're going to say for each W in words, let's stay with the first word, which is Emma. Same thing as before. I've done this like a gajillion times by now. I'm going to add the starting character and the ending character. And then I'm going to do the same thing for each first character, second character in zip of characters, shift by 1. You can see this is the same thing as before. I basically have my bigrams. And now what I'm going to do is the same thing. I'm going to grab my indices that are right here. Those are the indices. And basically, I want to store in my x's the first index, and in my y's, the second index. So basically, and let's go ahead and chuck x's into a tensor of x's, and we'll do the same thing with y's. So this is my training data set. What did I do? Sorry, just one sec. Let me just copy paste this. Yeah. I'm not going to go into what that reason was. Don't worry about it. But basically, you can see that X's is my input data and Y's is my output data. So I want to construct a neural network that is going to take as input these indices, which is start character, E, M, and A, and is going to predict the next token, which is E, M, and A, right? And then of course, N token, right? Now, what's the big problem? The problem is that how the hell are we going to train a neural network that's going to predict as output probabilities? Neural networks don't work that way. Neural networks can predict, for example, they like multiply these weights and they add them together. Sometimes the output of neural networks is like positive. Sometimes it's negative. The output of neural networks definitely doesn't sum up to 1, right? So neural networks basically violate all probability, all rules of probabilities. They don't respect the nice, neat rules of probabilities that I wrote up here somewhere. Where did I write it? I think I wrote somewhere. Probabilities add up to 1. Probabilities are negative. I'm going to put this in Markdown. This is like so important, right? Neural networks don't respect these rules. Like if I have a neuron, it can train its weight to do whatever the hell it wants. So that's problem number 1. Problem number 2 is it's probably a pretty terrible idea to take a neural network and to train it as input on indices. And the reason is if you remember the image of a neuron that I had pulled up right here, these neurons, they're basically, trigger happy, right? And if you give them an input of, let's say, 13, the 13th index, the 13th index isn't like 13 times more important than the first index, right? So inputs to neural networks need to be linear in some way. If the number is higher, it needs to indicate that that's a stronger activation. But if I were to simply train a model off of indexes and try to make it predict indexes, it would fail big time. And the reason is that neural nets want to make sure that the different inputs that you can have to the neuron, if they're bigger, that means there's a bigger effect on the model. So one more time, a larger index of 13 is not in any way 13 times bigger or more powerful than the index of 5. So we cannot dump these naively into a neural network. So we're going to do what's called one-hot encoding. One-hot encoding is where, and again, just follow along with the PyTorch for now, is that for this x vector that is 0, 5, 13, 13, and 1, there's 5 elements here. I'm going to have a vector that's 5 by 27. Let me show you what that looks like. This vector is 5 by 27. Let me prove it to you. X encoded. That's the shape. Each row represents one of the input characters. So this is the input character start token. This represents, what's it called? The E character. This represents M. And what we do is that we simply turn on a 1 for whichever character this represents, and we leave everything else as 0. So then does this kind of make sense? Do you see how now we're not like having like multiple numbers and different size magnitudes? We just represented the same data, but with more numbers. Does that make sense?
Yes.
Yeah, so this is called one-hot encoding. And again, this is something that neural networks work much better off of. You cannot train a model to take as input an index and predict as index, but you can certainly take a model to take a one-hotted encoded vector and to go on from there, right? So one hot, that's a function right here. It takes in a vector, it takes in a number of classes, and it basically returns a vector that for each of these elements, it'll be a 27 length 0 vector, and it'll turn on this index, right? So you'll see, for example, for if I do, what's it called? The second element right here, the fifth entry is on, right? Awesome. Let's be sure that we are xinc.dtype. I want to make sure we're in float 32 because we're going to train neural networks off of this. Now, let's go ahead and use a single layer neural network, which is simply defined as a weights matrix. Let's use the random function in Torch. That's going to basically take this is the random function. So this basically allows us to take what's it called? 10,000 random entries. And these are all torch.rand will use the standard distribution. So what torch.rand does is it keeps plucking entries from the random distribution. Now we remember from the random distribution, if I'm going to sum up all the entries and divide by the number of elements, the average of the random distribution is almost always 0, right? And the standard deviation is 1. So now we have a bunch of standardly normal weights. We actually don't want this stupid shape. We want to have it as 27 by 27. Okay, so what that means is that when we do a multiplication of our data, which is in this case 5 words that are each 27 long, multiplied by our weights, which are 27 by 27, we're going to end up with an output that is 5 by 27. That's how matrix math works, is that the middle dimension gets deleted out and you end up with the outer 2 dimensions, right? So what that's going to mean is, again, I'm going to just write this over here very clearly, is this one layer neural network is going to predict, basically we want it to predict the probability distribution. Now, what did I say? We cannot have neural networks predict probability distributions. If we did this, if we did X inc at W, oopsie, I need to make sure this is 27 by 27. And now if I do X inc at W, these are not probability distributions. First of all, this thing, each element, it definitely does not sum to 1, right? That's cooked, right? It's not summing to 1, right? If I look at any other row, it's not summing to, oh my God, we even have some negative numbers in here, right? So this is not a probability distribution. This is really bad. So we cannot have a neural network output a probability distribution. They're just not designed to do that. Okay, cool. Let's think. If we can't have a neural network output a probability distribution, how can we work backwards and generate a probability distribution from the output it does generate? Fazan, you're with me so far, right? You agree with me that neural nets don't generate probability distributions?
Yes.
Yeah, right. And the reason is probability distributions add up to 1, and probability distributions cannot be negative, right? And neural nets don't give a shit about those rules. They'll do whatever they want, right?
True.
Okay, so let's keep going. Okay, so how can we work backwards? How can we transform the data that comes out of the neural net such that it becomes a probability distribution? Well, what if I told you this? Previously, when we had this 2D array, these were counts, right? Counts are always positive. What if instead of thinking about our weights as counts, What if we thought of them as log counts? Remember, if I have a function log of x can be, it ranges from negative infinity all the way up to positive infinity. It only takes in positive numbers as input, right? Log of x is really useful here. Just like counts cannot be negative, log counts cannot be negative. The only difference is that, log counts cannot take in, an input that's negative, but their outputs can be whatever, right? So let's just say, all right, guys, let's try and train a neural net that doesn't predict the counts. It predicts the log counts. Okay, okay, okay. Let's come up with a word for this. Let's call log counts logits. Let's just call log counts logits. You're gonna see this word come up over and over again in machine learning. Logits, right? Well, if I have a log count, how do I turn a log count into a count? Well, I just do e to the log count, right? So if I do e to the log count, I'll end up with counts. Okay, all right. So I'm basically trying to say my weight matrix represents my log counts. If I take e to the weight matrix, I'm going to end up with what I'm trying to predict are my counts. And if I normalize those counts, I'll end up with my probabilities. So I'm going to show you that one more time. My W is supposed to be a neural net that gets the log counts. We want my neural net is not capable of predicting counts, but it can predict log counts because log is free to go negative, positive. It doesn't have any problems. Let's try to train a neural net that predicts log counts. If I do e to the w, that's going to be the counts. And if I do e to the each, for example, given lowercase wi, that's the vector. And if I normalize it by basically e to the w, this thing over here is the normalized exponential counts. If I search up softmax, it's exactly this function, right? So if I try to train a neural net whose output layer is each of these values, and remember, these values can be anything. They can be positive, negative, a gajillion, a billion, whatever, right? And if I take the exponent and if I divide by the sum of the exponents, I will end up with a normalized vector that sums up to 1 that won't have any negative numbers. Boom. That is going to be my probability distribution. So let me show you what that looks like. So I'm going to grab this one more time. W is equal to torch.random, X encoded, multiplied by W. I have all these negative, positive, ugly numbers. Let's say we now take that multiplication and we raise it to the power, we do e to the power of all those numbers. And then, let me just write this over here. This is my logits, multiplying them. These are my counts. If I do X and add W, and again, all these counts are totally wrong. I didn't train my neural net yet, but roughly, these are my counts. You can see, all right, the counts have decimals to them, but, it's pretty good. And now if I normalize them, the probabilities are going to be counts divided by, and remember, counts dot sum, we want a row-wise sum. That's why we use the dimension as 1, and we set keep them equal to true, right? So now if I look at the probability, this is my probability distribution. And to prove it to you, none of the numbers are negative. And if I take a given row, and if I take the sum, it adds up to 1. Okay, so now what do I have? I have a random weight, which I have this weight matrix. It's all random. It represents a single layer neural network. And then I apply the softmax function on top of that output layer to generate a probability distribution. All right. Fizan, is it okay if we just go like 5-10 minutes over? Is everyone fine with that?
Yeah, sure.
Okay. Is everyone with me so far? Do you guys see how we're taking the output of a neural network and we're generating probability distributions? Is that cool? All right. You guys are with me. Awesome. Let's keep going. All right, now I know how to train. I already know from last time how to train a neural network. Now I know how to turn it into a probability distribution. Let's also keep in mind that e to the x is a differentiable function. Taking the average is a differentiable function. So if I use something like AutoGrad, which I developed last week to train a neural network, guess what? I'll be able to use backpropagation, take the gradient, do gradient descent, and decrease my loss function. And now we're going to go absolutely sicko mode. So let me do, okay, neural net training time. All right, guys, I'm going to do this in 10 minutes. This does not matter. This is basically all extra credit. I mean, like, it's just, you guys don't have to code this, but I'm just going to do this really fast for you guys. There's my weight matrix, right? Now what I'm going to do is I'm going to grab my one hot encoding. I'm going to multiply it by my weights to get my logits, raise it. I already did this before. I'm just putting it all in one place. Take my counts, take my probabilities. This is called a softmax, right? And now what I'm going to do is I'm just going to output for you guys this little bit of code. What this does is we are going to take each given bigram, dot E, EM, MM, MA, A dot, and we're going to say, what are the output probabilities our neural net predicted? This is what I showed you before. These are the result of the softmax. This is the probability distribution we generate. I'm going to calculate the probability that is assigned to the next character. And I'm going to grab the log likelihood and then the negative log likelihood. And finally, I'm going to tell you that for my neural net, which has totally random weights, what's my loss function? Well, my loss function in this case on totally random weights is 3.7. That's my average negative log likelihood. And we covered last time, how do you train a neural network? Well, let's focus on doing just one optimization of the neural network. First, I want to do my forward pass. Actually, let me first get a new, sorry guys, just 1 second. So let's do one training run. So this is 1 second. If I do one optimization here, this is gonna be really cool. I'm gonna do a forward pass, and then that's my loss right there. So where my loss was like 3.7. Then I'm going to say, okay, w dot grad is equal to none. I'm going to set the gradient to be 0. And remember the function that we made last time in lecture 1? It's called dot backward. I'm going to calculate the gradients. So now when I do w dot grad, it's not none. It's this giant gradient thing, right? It's mostly empty. It's fine. And I'm going to do w dot data. I'm going to take the gradient. And remember, the gradient is the direction of steepest ascent. So if I multiply 1 by the gradient, let's actually multiply 0.1. Let's not walk too far. If I walk alongside the gradient, like, sorry, if I walk down from the gradient, that's the direction of steepest descent. And now you'll see, previously the loss was 3.7. Now it's going to keep going down. So if I print out the lost here, there we go. See how the more I run these cells, do you guys see my loss function is decreasing? So my weights are being updated based off of my loss function, which is the mean square, like mean, negative, log, likelihood, whatever. I just use AutoGrad to calculate the gradient. And look at that, guys. My loss is going down. So now my neural net is fitting to this data. And finally, I'm going to grab, what's it called? A little bit of code here. This is a code that takes, let's not just one optimization. Let's do the above code in a for loop. All right. So we're going to grab that. This code is same thing. It's doing the forward pass, it's doing the backwards pass, and it's doing it right here. And we're going to print out 5 gradient descents. Let me just one more time get some random weights. Num is not defined. Sorry, guys, just 1 second. Let me make my data set one more time. Oh yeah, we got to do this for all the words. So XS and YS, previously they were only 5 elements long because I only had 5 words. I'm going to now do all the words. And basically, so I have 228,000 words. And now watch this, guys. Boom. See how quickly my loss went down? Let's like keep going. I'm going to adjust my learning rate slightly. Let's set this to like -10. It's a little bit slow. You can see I'm running this on my MacBook. But see how the loss is going down? See how loss is Let's run that one more time. The loss starts off at 3.75 and it makes its way down to 2.69. So I'm training my neural net. And do you guys remember what was the loss that I achieved all the way back here with my model? I think I was able to get it down to um, I can't remember. I think it was like 2 point something was the loss that I achieved on counting the probabilities, right? And now we're getting pretty close. We're at 2.6. If I keep training this thing, let's like keep going. If I do like 500, I don't know what'll happen. Oh my God. Okay, it's going, it's going, it's going, it's going. My loss is decreasing. My neural net is training. I'm getting really close to 2.4. Unfortunately, I'm not going to be able to go lower with that with this current architecture, but I'm basically stabilizing at the previous loss that we had calculated for my entire data set when I did the simple bigram model. All right. So now let's use these weights the weights that I have, I'm going to use the same code that I did previously, and now I'm going to call torch.multinomial. So before, remember, I would grab probability distribution. Now I'm going to run the forward pass using my weights, and I'm going to call torch.multinomial, and let's see the words that come out. Sexy. There it is. My neural net, I trained it such that it's basically equivalent to counting probabilities, right? And that's basically today's class. So I'm gonna say a couple notes at the end of it. There's a bunch of I think cool reflections that we can have as a group if everyone is down to stay just like 10, 11 more minutes, or like 5 or 10 more minutes. But Fazan and the chat, any questions so far? I know I rushed that last piece, but hopefully you guys saw, I just trained a neural net in real time. That's a bigram model.
Oh, this is so interesting. I've never seen a, a neural net chain like this. So, uh,
Yeah.
it's
So
very
again,
cool to
guys,
see
the
it.
code that I pasted was just a for loop that did the thing I was doing by hand. So see, by hand, what I was doing is I was running this cell that makes random weights, and then I was doing one forward pass. The forward pass was what I told you guys. One hot encode the data, and then multiply it by the weight matrix. My weight matrix makes that output layer right here. Slap a softmax onto it so I get a probability. And then with that probability, calculate the negative log likelihood. You don't have to like this was just a one line. Forgive me. If we use the same code that we did previously, you would get the negative log likelihood. But you can see here that oh shit. Just 1 second. I need to, I'll fix it in a second. I can't remember let me just kill my kernel and restart. But you can basically understand the idea that, we were basically decreasing our, actually, that's actually like kind of pissing me off. Oh, I need to initialize these vectors again. Just 1 second, guys. I gotta pull in all this data. Oh my God. Uh, Basically, this code right here is doing exactly that, where I can grab my x's, I can grab my y's, right? And then I can train my neural net. And all my neural net is doing is that forward pass right there. It's calculating the loss. If you guys remember, the whole point of last lecture was what's loss dot backwards. That gets my gradient. And then w.grad, which was previously none, is now assigned and I can now update my data and push my weights of my weight matrix down the gradient descent, which decreases my loss. And I can run this like for 10,000 steps or for 1,000,000 steps. I'm not going to be able to go below 2.4, which is the counting model we predicted. Okay, let me answer all the questions in the chat. Okay. Should we read any papers that dive deeper into the math of how this works? Yes, you can go to d2l.ai and you can search up uh, d2l.ai log likelihood, and you'll go to chapter 4, and you'll see basically they explain all of this, but I did a way simplified version of this. Okay. Um, all right. Should we need so this is simpler than weights plus biases, but this still works because the loss is differentiable. Yes, there's no biases in this matrix. I could have added biases as well. I would have had an even better time. Yeah. Um, will we be improving this model in the future so it doesn't output gibberish? Yes. Now that we have a neural net that can take one character and predict the next character, it's so easy for us to train a neural net that can take the first two characters and predict the next character. Or, for example, predict the first three characters. So what we're going to work on is we are actually going to implement in the next class a paper that was written in 2003. It's called Neural Probabilistic Language Model by Bengio in 2003. I'm going to have Faizan send you guys this paper before next class. You guys, this is kind of complicated, but I'm going to walk through this next time. And this paper basically walks through a neural network. That neural network takes in a given token, it turns it into a vector that's one hot encoded. It puts a bunch of layers in between, it applies a softmax, and it predicts the next token, right? And that's exactly what we did today. But today, instead of using just, see how this is doing, for example, 3 words as input? This is called a trigram, sorry, a quadgram. There's 3 input tokens that lead to our fourth. That's why we call it a quadgram. Today, we implemented a bigram where you only take in one token and you predict the next token, right? Yeah.
Mhm. Wow.
Okay.
Was this one of the papers that like put Yashua Bengio like on the map?
100%. Yeah. So basically, this is one of the most influential papers in machine learning. These are not the first people that, so this paper, I love it because it has a bunch of concepts in it that are very relevant. But basically, this paper tells you everything you need to know about probabilistic language modeling. So before this, people really weren't using neural networks to predict the next word. And again, remember, today I was working on a name generator. So we were working on a character by character level. These guys are actually working on a word by word level. So if you read their paper, you'll see they have a vocabulary size of 17,000. Let me just search up what's the vocabulary size of GPT-3. Okay, so GPT-3 has 50,000. Okay, there's 50,000 words in the English language that GPT-3. These guys had a much smaller model. It was just 17,000 words. Their features were 30. So, for us, our characters were just an index. They had, what's it called? Much larger features. And now we're going into real extra credit here, but the purpose of this model was not even to predict the next word in a sentence, even though you do see them doing that. So what they're trying to do here is, let's say, for example, you have 2 input data streams. The cat is walking in the bedroom and a dog was running in a room. Okay. They wanted to be able to predict if we had the cat is running in a blank, and let's say the model had never seen these words before. The cat is running in a blank. They wanted to be able to predict that next word, right? So that's word prediction. That's pretty straightforward. But why did they want to do that? You might be thinking, okay, why the hell would someone want to make a stupid model that predicts, complete the next word? And again, this is back in 2003. So the language models were not good enough that they could like code algorithms from scratch. The reason was they were working on something called word embedding. And basically, you can see here, if the cat is walking in the bedroom is in our training data, and also in our training data is a dog was running in a room. If we then have in our test time the sentence, the cat is running in a room, that basically tells us that cat is similar to running is similar to room. This is called semantic similarity. So the way that words are represented in GPT-3 or GPT-5 is you take a word and you do what's called word to vec. You turn it into a vector. But the really interesting thing about word embeddings is that similar words will be clustered together. And in fact, you can even perform math on word embeddings. So what's really cool is if I take, and we're going to do this 2 lectures from now. If I take the word embedding for king, and if I take the word embedding for queen, and I subtract them. So king and queen, what's the difference between king and queen? One is a man, one is a woman. If I take uncle and aunt, the word embedding for uncle and the word embedding for aunt, and I subtract them, the difference between king and queen and the difference between uncle and aunt is the same vector, right? So how the hell did they design these word embedding spaces such that the vectors encoded mathematical meaning? The way that they did it is that they built these neural probabilistic models that would predict the next word. And then we're going to talk about in a second, once you have a next word predictor, how does that tell you which words are more similar together? Okay, awesome.
Wait, Saad, this is actually very interesting because if they had this in 2003
Yeah.
and then ChatGPT came out when like 2022.
Yeah, 2022, 2021. Yeah. It
Like,
happened in those
why do
4 years.
you think it took that long when they were kind of this far in
Yeah.
2003? With the hardware limitation, was it?
Yeah, it's a couple
What
of
was
different things. So first of all, since the 1970s, there's been what's known as the AI winter. So for example, last time we talked about a neural network. Neural networks were invented in 1970s, basically, the perceptrons, the multi-layer perceptrons. Yann LeCun is famous for convolutional neural networks, right? And what's happened over and over again in AI, historically speaking, is there's been 3 to 5 years of the AI summer where there's like a big rush and people invented neural networks and like for example people invented language models or for example there was like a big exciting new advancement and then for 10 years there was silence. So this happened in the 70s, it happened in the 80s, it happened in the 90s, it happened in the 2000s, it happened over and over again where in every decade we had 3 years of a crap ton of AI research and like 7 years of AI winter. So that's one interesting thing. Why does that happen? That usually happens because we will develop a new AI model and we will work on it and we will work on it and work on it. At some point, we will realize either we don't have an architecture that's good enough to, take the next leap forward, or we don't have hardware that's good enough to take the next leap forward. So the first open question is an AI winter coming for us? Right? We've had a couple years of AI research for some time. So historically speaking, if history tracks, 2028, there should be no more AI research, right? Because if history tracks, as we've seen in the past couple decades, you have a bunch of AI research and you have like a silence for the rest of the decade, right? That's one thing. The second thing that you asked is, what the hell happened between 2003 and 2010, right? So 2003 was the end of the beginning of one AI winter. What happened was is that we didn't have GPUs. So there was a company called NVIDIA. You might have heard of them. And they made gaming consoles. Like I feel like when I was a kid, the only people that knew about NVIDIA were gamers, right? Like I remember when we were a kid, you remember this, Faizan? We would do like first FPS like shooter games. And the only
Yeah.
people that knew what the hell an NVIDIA RTX was were those like stupid kids that were playing video games all the time that were doing
Or
like
crypto people?
Dota 3 or crypto mining or whatever. Okay, so Faizan, why do you need a GPU if you're playing video games?
The video graphics are very computationally.
Exactly. Video graphics, when you're playing a video game, are all matrix multiplications. So there was a guy in 2011 named Alexei something something, I forget his last name. He invented what's called AlexNet. There's a paper that came out, and we're going to go through this if we keep doing this series next month. AlexNet was an image model, and Alexei's main realization was he was working on image models, and he realized, oh my God, we don't have enough CPUs to train these things. The hardware is not good enough. And he was looking, and Alex loved to play Dota 2. You guys have heard of Dota 2, Dota 3? So he loved playing video games. So he realized, wait, these same GPUs that are doing matrix multiplications for computer graphics a gajillion times a second, these same GPUs can be used for machine learning. So then AlexNet was the first ML paper that showed that you could use GPUs to unlock the next level of AI. Because then when you have enough parallelized compute, you can actually train larger and larger models. So then in the early 2010s, we had a revolution where we had a bunch of image models. And then, for example, you might have noticed in 2015, the Tesla Autopilot program is started. And because we have better vision, Waymo, I think, is like a 2013 project. So now we have image models that are like getting really good. And then the critical unlock is OpenAI basically in 2021 comes up with RLHF, reinforcement learning with human feedback. And they basically say that the answer to the next AI summer is take the same number of GPUs that we have and throw the entire internet on it. And they train GPT-3 for like, I don't even know, like a year on like tens to hundreds of thousands of GPUs. No one had trained a model on more than like 2 or 3 thousand GPUs before. I mean, honestly, even today, people don't train models. Even Meta, when they do their experiment, unless you're talking about like the largest llama models, but like Quen 32B or like Llama 32B, you really only need 1,000 to 4,000 GPUs to train this thing, right? But GPT it was, the next unlock where they used. So that's just some of the history. Forgive me, I was kind of
No,
rambling.
I mean,
Uh,
I don't know. I find this like very fascinating. I hope the people here do too.
yeah.
I mean,
Oh
it's
yeah.
crazy because
Yeah.
now, like Google is training models across multiple data centers. Like that to me is like unbelievable, the amount of
Yeah, I mean,
engineering.
so
behind?
That's a couple things. So yes, Google does have multiple data centers. It actually isn't the most efficient to train a model across multiple data centers. It'll take a long time, and the reason is because most of the time in machine learning is spent in network costs. So in moving gradients around. So this is very interesting because we talked about gradient descent and we programmed AutoGrad together as a group. Can you imagine if you ran AutoGrad, that little tiny file, not just on one GPU, but on tens of thousands of GPUs that are connected by these NVLink spines, right? Like these like long Ethernet cables. It's actually like the slowest thing in machine learning is what's it called? Um, sorry, just one second. The slowest thing in machine learning is network time. GPUs are really fast, but it's actually transferring data is the really difficult problem. So the reason why Google has hundreds of data centers that have so many GPUs is not because of training, it's because of inference. Is because they need to have a crap ton of GPUs because so many people are querying Gemini at a time. Now, training a neural net on more than 4,000 GPUs or more than, I think the most is like 10,000 GPUs is very unstable. And the reason is because you literally cannot do it. And the reason is that when you train GPUs when you train these modern machine learning networks, every GPU has to be connected to every other GPU. Okay, now, Faizan, let me ask you a leak code problem. If I have a graph of n nodes and it's fully connected, as in every node is connected to every other node, how many edges do I need?
Is the n squared?
Yes, n squared, right? So if I have 10,000 GPUs, I need 10 to the 4 times 10 to the 4, 10 to the 8 connections, right? So 10 to the 8 is 100 million. Is that right? I think so, right? So you can see, first of all, the connections absolutely explode, right? And it's actually really difficult to have 100 million wires between 10,000 GPUs in a data center. It's just not possible, right? So there's this thing that NVIDIA has been working on called NVLink Spine, NVLink Spine. And what this is basically is they take these rows of GPUs, they stack them in these, server racks, and they attach a bracket on the back that's called an NVLink spine. And this basically allows all of the GPUs in that server rack to talk to all of the other GPUs that are connected to this spine or are connected to other spines. And what's really cool is this thing has more throughput than the freaking internet. This has a throughput of, I think it's like 3.4 terabytes per second. No, wait, I think it's more than that. Throughput. Oh, sorry, 130 terabytes per second. And the entire internet, I think, is like 120 terabytes per second. Like all of the traffic of all of the internet of the entire freaking world is like 120 terabytes per second that's moving. And this thing does more than that. Okay, let me go ahead and answer some questions because people asked some stuff. Okay, should we read any papers that dive deeper? We're going to talk about this paper next time, and I'll have Fizan send it out. This is simpler than weights and biases. Yes. Um, Will we be improving this model in the future so it's not gibberish? Yes. Let me pick your brain. A random number generator that's not really random. A probability of the numbers would be 1 to 10 in each position. One with 3 places, one with 4 places. Can I ML model this? I don't know what that means. Okay, and then Mohammed Jain asks, how do they train the entire internet under one neural network or a bunch of them? How do we see different ones for code summaries? Mohammed, could you clarify what you're saying? I guess your question is how do they take so much freaking text from the internet and train a neural net on that? So this is what were those guys that had their own startup related to Git for ML?
Yeah, well, they're called gradient.
They're called Gradient. Okay, so
Yeah.
Gradient was talking about this last week. What's called FSDP, fully sharded data parallel, and TP tensor parallel. This is something we're going to talk about, inshallah. If I don't know what I'm saying, inshallah. If Fazan allows me to do this class next month, then we're going to do this as well. We're going to talk about, okay, we've been training a neural net on my MacBook for the past hour or two. But what if I had 1,000 MacBooks? How am I going to train a neural net? And there's two approaches. One is called tensor parallel, and the other is called data parallel. Tensor parallel is where you take the actual weights of your neural net and you replicate it. So let's say I go from one MacBook to 10 MacBooks. Every MacBook will get a copy of my weights, but the data that I'm training on, I'm going to divide it into 10. And each MacBook is going to get 1/10 of the data. And then what we're going to do is we're going to do a forward pass. We're going to calculate the gradient. And each of those 10 MacBooks are going to average the gradient. That's why every MacBook needs to be able to talk to every other MacBook so it can send the gradients. And then we're going to do the backwards pass. And we're going to repeat and repeat and repeat where each MacBook gets 10% of the data. That's called tensor parallel. As opposed to data parallel, where everybody sees the same data, but we take the layers of the neural network and MacBook 1 gets layer 1, MacBook 2 gets layer 2, MacBook 3 gets layer 3, and you arrange it like a chain. So basically, all of the data goes to all of the MacBooks, but each MacBook is only responsible for updating the gradients of 1/10 of the weights. So that is how these models are trained on the entire freaking internet, because the internet is just too much data for one machine to handle. So they take thousands of GPUs, 1 to 4,000, and divide it that way. So hopefully that answered your question, Mohammed.
Yeah. So I'm
Uh,
gonna have to head out, but please share. I mean, I can just share your LinkedIn there as well. When I drop mine in the chat, I'll share yours. Um,
oh, and also people, please post about this on LinkedIn.
yes. Okay. Oh yeah. You shared yours. I shared mine.
I can share my screen if anyone wants to take a picture or something like that. And I go down to right here.
And yeah, can you put this on GitHub and then share a link too?
Yeah, yeah, I'll send it to you.
Okay, sure.
Yeah.
All right. Feel free to take your screenshots now. I'm gonna end the stream in the Zoom in a bit.
Awesome. Zoom in a bit.
Yeah. All right. Thank you so much, Saad, and we'll see you next week.
Yeah, awesome. Thanks, guys.
And yeah, looking forward to it. All right. Take care, everyone. Bye.